The keynote address is about this topic, India's resilience to semiconductor supply chain. So, though it's digital, I think it's our duty to welcome Shri Shiva Shivaram. Yeah. Video, please.
Good morning. Good to see all of you. Good to see all of you virtually. It's evening here in Silicon Valley. Yesterday, the Prime Minister was admonishing us to be practical in our advice, practical in our suggestions for what we need to do next. So I want to thank Minister Vishnu and Minister Rajiv Chandrasekhar for giving me the opportunity to talk to you all today. Next year would be my 40th year in the semiconductor industry. There are some in the audience, Ajit Manocha probably is sitting up front saying that he has been here long and he calls me a young man. But over these 40 years, we have seen vast transformations in the industry. In the 70s, the United States led the semiconductor industry. In the 80s, the Japanese got to dominate the industry. In the 90s, the Koreans started in. In the late 90s and the early aughts, the Taiwanese started their semiconductor expansion. In the last 5 to 7 years, the Chinese have been investing a lot of money into the semiconductor ecosystem. There has been a pattern in these developments back and forth. There are lessons to be learned. There are models to be emulated. There are pitfalls to be avoided. I want to spend some time talking about all of these to you with respect to our ability to have resilience. Let me see if I can share my screen. I'm assuming you can see my screen. So we'll talk about how do we ensure India's resilience. How do we make sure that in the midst of all of these semiconductor shortages and security issues, what do we need to do? I talk a lot, and my lawyers think that they have to tell you that don't believe anything this man says. So I had to put that up front. Let me talk a few minutes about Western Digital, the company that I lead. Many of you know us. The SanDisk brand is very well known. We outsell our nearest competitor 2 to 1 in India. 40% of the world's data sits in a Western Digital device. There is a very large claim. 40% of your data, whether it is in your cell phone, whether it is in the cloud, whether you store it in your PC, 40% of the data sits in a Western Digital device. Western Digital is the world's largest pure play storage company. We have the portfolio breadth, 14,000 patents and 65,000 employees, including a very large development site in India. The Indian development site has grown almost 10 times in the last 7 or 8 years. We are a big manufacturing company. We are the largest foreign investor in Japan, period. We are the second largest foreign employer in Thailand. We have been continuously having manufacturing operations in Malaysia for now close to 45 years. We have operations around the world, including, as I said, in India, and these 65,000 employees send you their greetings. We know how important India is to the global ecosystem across, not just in semiconductors around the world. We are fully present and involved in India's growth. So we've heard this before. India is starting up. 60,000 plus startups, more than almost 5,000 that have been funded. 83 active unicorns. I'm told there are more, but there are 83 active today. Because if you go public, you're no longer considered a unicorn, you are now a public company. So 83 active unicorns today. What they probably all are assuming that there will be the infrastructure that provides them to function. That infrastructure, of course, is provided by semiconductors. Let's look at this a little bit more carefully. What does semiconductor resilience mean for India? What are the objectives? What are we trying to do? First and foremost, we need to ensure India's national security. In the broadest sense, I don't just mean defense electronics. I mean the national power grid. I mean the national communication network. We need critical industries to thrive. Automotive industries, telecommunication industry, power industry, and my beloved entertainment industry. I need to be able to watch Dhoni and CSK win once more. I want to be able to watch my Bollywood movies. So entertainment industry. These industries, for them to thrive, you need to have semiconductors below them. And of course, data digitization are causing new creative transformative industries. Soon we'll have quantum computing. Soon we'll have DNA-based storage. We will have data-based new applications created. We need to lead all of them. And in the end, for the common man, we need to make sure there is manufacturing jobs that are high-paying, high infrastructure, high economic returns. So these come naturally. These are our overall objectives when we say we need to have resiliency in India. Where is all this data coming from? I took a look at it. In the last year and a half, just during the pandemic, there have been 17 applications with over 1 billion downloads and 37 applications total over time that have had more than 1 billion downloads. India has been downloading everywhere. Every one of these is producing data. Every video camera, every cell phone, every surveillance, all of these are producing data. And these data are producing a flood of growth. So here it shows how much these data is growing. The hard drives and the solid state drives are exploding in demand. Almost 37-35% year-over-year CAGR. To top it all, the amount of data that is actually stored is only 7% of the data that is actually produced. So we produce close to 118 zettabytes of data. For those of you who keep track of these things, a zettabyte is 10 to the 21 bytes. That's about the number of stars in the galaxy, 10 to the 21. That's the amount of data we are producing. And we are not storing a lot of it. And we need to figure out technologies to be able to store all of them and gain value. In order to gain that value, every bit that we produced, ultimately somewhere, someplace, a physical bit has to flip. Somewhere somebody has to store it. Then somebody has to go network it. Then somebody has to process it. That bit in the end becomes valuable only when we are able to process it, and that processing happens with semiconductors. Let's look at the semiconductor industry overall. Today, if I looked at the industry, it's about a $500 billion industry. Memory is the biggest component of it, followed by microprocessors and other application-specific integrated circuits like RF, wireless, power management, etc. And then an assorted number of minor categories like discretes, optoelectronics, non-optical sensors, analogs, chips. Put them all together, you get this $500 million of revenue. Memory is about more than or about a third of the revenue. And that's where we are talking about the amount that needs to be stored. The technology uses each of these, the fabs, in a slightly different way. A memory, every generation that comes in replaces the existing technologies in the same fab and makes the same fab more advanced. Logic moves to a new fab, lets these old fabs get used by other applications. And these other applications use more depreciated fabs. Each one of them has a different way. Each of these big components uses the fab differently. And into these fabs go the capital equipment. And this marketplace is about just under $100 billion. The biggest, of course, we hear a lot about lithography. Lithography, where these machines could be $80 to $100 million each. Materials removal, deposition, process control, these kinds of $2-3 million pieces of equipment go into each fab, leading to about $10 billion of equipment going into each fab. And so the equipment industry is a critical part of that supply chain. In the semiconductor world, the closest to the original prophet is Gordon Moore. Gordon Moore one day went up to the mountains, prayed to the semiconductor gods, and came back and gave us our rules. And he gave us 2 rules. The first rule, the so-called Moore's Law, talks about scalability. He said semiconductors are unique in the world. Every year on the same real estate, you can get more. Scalability is our ability to get more out of the same resources. We've been doing that now for 60 years. Scale, on the other hand, is our ability to use that scalability and propagate it up, make it much bigger. I'm going to talk to both of these, scale and scalability, with the context of those storage systems that we talked about. About 30% of all semiconductor revenues is memory or storage, and I'm going to talk about how the scalability and scale work, and you can now extrapolate it to other systems. So let's talk about one of the places where it has grown a great deal. This is DRAM. DRAM is used for storing those bits during processing. You can see as the data centers exploded around the world, DRAM production just exploded. It's continuing to grow. This looks very impressive till you look at how this looks in the presence of flash. That same DRAM in scale looks minuscule compared to how fast flash is growing. Flash is growing almost 3 to 4 times more than DRAM is going. And above that is hard drives. Hard drives and flash provide storage. They are 30 times more than DRAM and 2 times more between flash and hard drive. This is the scale. Those zettabytes that we were talking about has to be stored in one of these 2 things. Look at what this means. The flash NAND wafer production, you take the wafers annually produced by the NAND manufacturers around the world, you stack them one above the other. Just 1 year's production. Compare them to some well-known landmarks. That's the Eiffel Tower. You think, it must be about as tall as the Eiffel Tower. That is the Eiffel Tower in that scale. The Burj Khalifa is there. The annual NAND production is bigger than Mount Everest in height. The annual NAND production of wafers, if you just stack them, 12,000 meters, is a third bigger than Mount Everest. That's scale. That's how much these fabs are producing. I want you to give us an idea of how big the scale of these fabs is. We operate one of the world's largest fab complexes in Japan. This, next to Intel and SanDisk in Santa Clara, is the Levi Stadium where the San Francisco 49ers play football. Large stadium, almost 1 lakh people, 100,000 people can sit in it. Big stadium. Look at the size of it when you compare it to the size of the fabs that we have in one site in Yokkaichi, Japan. We need the equivalent of 9 stadiums that would fit in that one complex that produces 1/3 of the world's flash. That 12,000 meters of wafers get processed, 1/3 of it get processed through this. That, I want to make sure you understand, is scale. Those wafers then have to be then made into products. The USB sticks that you have in your hand, the SSDs that go into the data centers. The wafers come in, get assembled, tested, packaged, system integrated, and shipped out as product. In a typical day, almost 5 million die get processed within Western Digital. 5 million per day. In a week, 1.2 million SSDs get processed in that factory, which has got wafers in, SSDs out. So I want to make sure you got a sense of what scale is. This is what we need to reproduce in India over a long term. This is what we mean by scale. Now let's go to what scalability is. In that wafer is our ability to store the bits. I'm going to run a small video so you can get a scale of what's on that wafer. Let's see if this plays. It doesn't quite play like a video as I would have expected it to. So what it shows is 1 trillion of these holes that are as tall as skyscrapers on which these bits are stored. This is where the semiconductor equipment that is used to produce these layers, deposit, etch, and drill these holes are done. And you can see the progression of these skyscrapers over the last 10 years. In 2016, we made 48 layers skyscrapers, and now we are about to introduce 200 plus layer skyscrapers. This is the Moore's law on steroids. Whereas in logic, Moore's law is slowing down. In flash, Moore's law is actually ahead of time. Every 18 months, if you can see, 2016, 17, 18, 20, 22, every 18 months, a new node is coming in that can store 50, 60% more bits on each wafer. These are coming into high volume production, and those high volume production happens with wafers. Those wafers are on those mega fabs, and that mega fab produces that Mount Everest tall number of wafers. This is how scalability and scale work together. In India, if we can't get to a place where there is both scalability and scale, we would have failed. So the complexity of the semiconductor supply chain is the following. We talked a lot about what happens pre-silicon. Design, CAD software, IP blocks, simulation environment, emulation environment, verification. All of those things India is very good at today. We know how to get it done. Pre-silicon, we are good. Silicon processing, this is where fabs and capital equipment and materials. The fab, you can't think of it just, hey, I'm going to build a fab. The fab is more than a building. The fab is a business model. Given the capital intensity and cyclicality, requires a steady revenue growth so that this can pay for itself. It is a R&D receptor. It needs a constant flow of R&D to keep the scaling and scalability working. It is infrastructure intensive. Power, water, natural gases, waste recycling, people. We need to have the infrastructure that needs to be there. And of course, needs advanced personnel to run, maintain, sustain, and grow this. And once the silicon processing is done, post-silicon, packaging, assembly, test, system integration, application support. And remember, each of this is specific to those various categories I talked about. Whether it is memory, whether it is flash, whether it is DRAM, whether it is logic, whether it is ASIC, whether it is power, whether it is high voltage, high power, low power. These are different for these, analog. And this semiconductor supply chain is what we need to recreate. So let me conclude with how do we focus on this in a big picture. Today, no one country has all the pieces for a semiconductor self-reliance. It's impossible. Materials come from one place, equipment comes from another place, technology comes from another place, design comes from another place, finished product goes to a different market. Every place is different. So, the first and foremost lesson is security comes from well-developed alliances. We need to make sure that we are well allied with friendly countries and friendly companies and friendly nations and friendly corporations and multinationals so that we have security, because we can't do all of it ourselves. We shouldn't try to do all of it ourselves. But we need to be aware of the needs. What specific industry is so important to us that I need to make sure that we have that ready. We need to play to our strength. Our strength is our people. We need to play to our strength. And we really want to make sure we establish roots of trust in the supply chain. Defense electronics in particular, having secure fabs to make sure we know where we are getting our semiconductors from, that I can trust that supply chain. That is very important. Wayne Gretzky, an immortal hockey player, used to say this. Why are you so good at hockey? Somebody asked Wayne Gretzky. He says, you know, I skate to where the puck is going to be, not where the puck was. For us in India, it is important that we realize we need to know where the puck is headed. And we want to make sure we focus there as opposed to doing something historical. Where we were before the pandemic is not where we are going to be. We need to make sure we are looking forward and not backward. And this point gets lost often. Japan used to be a leader in semiconductor till they focused entirely only on the production of semiconductors and lost sight of the applications and the markets. They did not develop their own markets. And soon enough, the companies that were leading at that time, the NECs, the Hitachi, the Toshiba, the Mitsubishi, the Panasonic, lost their leadership in semiconductors. Leadership in applications and markets need to be there if you want to have the continuity of the industry. So if you think about it in a big picture, we don't want to do everything ourselves. We want to make sure that our well-developed alliances, we need to know what is important to us so that we can play to that strength. We want to make sure there is always a supply chain root of trust. Think forward, not backwards. And I want to make sure we focus on the leadership in applications. So I have given you a few ideas of what it means to have security in semiconductors. Our semiconductor religion is based on scale and scalability. We need to make sure we are enforcing. We are looking ahead. We are making sure we are developing those alliances so that we can leverage the immense strength of our people to lead for the long term in the semiconductor industry. Thank you so much.
Take questions. A couple of questions can be asked to him. Yes, and you can raise your hand, the mic will come to you. Mr. Shiva, can you hear us?
I can hear you very well, thank you.
Yeah, okay. Anyone? Yes. There.
Mr. Shiva, this is Raju Koduri from Intel. Nice talk, really enjoyed it. You started off with saying Prime Minister Modi wanted some practical advice, practical solutions. Unfortunately, I missed his talk, and I'm talking right after you, and I was a little worried how practical my asks would be for here. But I have to ask you, right, that after, now I want to ask, can we build your memory stack of the size of Mount Everest and solve all of India's storage needs? Is that something we should, is that practical?
So I have been talking with Minister Vishnu or Minister Rajiv Chandrasekhar about these things? I'm willing to dream. I'm willing to come here and say that a fab complex in India is indeed possible. People say pioneers get shot with arrows, but somebody has to be a pioneer. There's a often repeated joke in the Silicon Valley that says that I don't know what comes first, peace in the Middle East or a fab in India. I'm now willing to say that we probably will beat it. We will have a fab in India, and we will have sooner than later a fab that we would be proud of having in India. Did that answer your question, Raj?
Yes.
Thank you, Mr. Shivaram, for... There's one final question. Yeah, go ahead, sir.
Dr. Shiva, I was looking at your map of manufacturing sites. There is one red dot missing there.
You now know why I'm here. I'm talking to you. I'm talking in front of all of the ministers. We have a very large development site in India. Our engineers there have been asking me the same question. India has been, our employees, our contributors, our partners in India, we are getting folks from all the major institutions, the IITs and the NITs here. And we measure their productivity today by how quickly they produce a patent. And India has been now setting records, new college graduates from the time they come into the company to how quickly they produce a patent. We've been very, very productive there. Now it is time for us to seriously think about how we can go from a development site to now actually making the products that they are designing and developing and marketing. So we are looking at it, and I'm glad you noticed the absence of that red spot in the heart of India.
You can do also. Michael, yesterday people mic'd up, right? No, you can do that.
Shiva, this is, good morning, Rajiv Chandrasekhar. Thank you for that excellent presentation. On some days I require a boost and some confidence as well when on this mission that we've set out on, and this presentation was extremely, confidence boosting even for us. Quick question, what are the issues that you see for somebody like Western Digital when you look at India and consider or evaluate making an investment in a fab? What are the top 2 or 3 issues that you think we should be focused on?
So, Minister Chandrasekhar, thank you for having me here and allowing me to talk. People talk in terms of infrastructure first. Or can you have water? Can you have the land? Can you have natural gas? Can you take care of the waste? Can you produce the power? They are needed, no question. The infrastructure with respect to how do I have a capital equipment maker come and have his spare parts ready? Can I move it in and out of customs very quickly? Can I deliver it? Yes, these are solvable problems. What I do need, however, is this: a motivated, talented work base that I can count on from all levels, from operators to technicians to sustaining engineers to development engineers to PhDs and material scientists and physicists that need to come through. When I have that infrastructure reproducibly here, they will solve all my problems. In the end, all problems are people problems. People will always solve the problems. That's my confidence here, Mr. Chandrasekhar.
Thank you. Thanks, Shiva.
We now move on to the next keynote, which will be presented there addressed by Mr. Raja M. Koduri. He's already here, Executive Vice President and General Manager, Accelerated Computing Systems and Graphics Group at Intel. So, hearty welcome to you, sir. It's all yours. Yeah.
Thank you. Can you all hear me okay? Okay. Good morning. Need some energy. Good morning. There. I need it because I'm a bit jet lagged. I've been in, this is my 4th country in 5 days. And so I have some interesting stuff to share, but what I wanted to start off is actually, I get in trouble whenever I speak, when I'm in jet lag particularly. Okay, I'll tell you one such incident where I got in a bit of trouble. Anyone knows which country this is? Oh, good, good. So, in 2018, October, all of the interim CEO, Bob Swan, and the executive staff visited Israel. And we got to go see the Prime Minister, Mr. Netanyahu, back then. And, it was, pretty high-stress affair. It was an all-day thing because you had to spend 4 hours in security. Like that, the entire, they call it the sanctum sanctorum of entering the Prime Minister's thing. And, by the time we got in and all, you can see me hiding in the back. I really didn't want to be there, right? It's just, it was a ceremonial thing and you need to be there. And then we all got in his main conference room, okay? And there were like, TV, cameras, crews, and it was pretty hot too. And I found a spot to hide on the whole, in the conference room. And our CEO was sitting right in front of the Prime Minister. They were talking, and I was in one corner, and I couldn't really hear what was even going on, right? It was a bit distant, and I was dozing off in that corner. And suddenly I hear my name say, Prime Minister asked a question, and Raja, you should answer it. And I was like, what? I heard it kind of half, and it was something about AI, right? The whole conversation was going on like in Israel. It was an impressive country, right? I mean, Intel and Israel have a lot of history together, and I don't need to talk, say much about Israel, but, it's one of the, countries to look up to, even though they are a small country, right? The type of investments they do, the innovation that comes out of that small country is all impressive. But the question, I later kind of heard actually what the question was. I answered without really hearing his question. The question was, the Prime Minister was concerned, despite the progress Israel has made on AI, is Israel ever going to catch up with likes of Google, likes of other big private companies, the public companies that are growing at much faster rate? And is AI already won battle? So I said something. You can say anything about AI back then and it's true, right? Just like cryptocurrency today. Somebody, wants to comment on cryptocurrency, you can say anything. Just say anything and it's all true, right? So I said something, and the Prime Minister said, I really like the answer. Now let me ask you another question. And he asked this: who will be ahead in AI technology by 2030, India or Israel? Like he said, over the next 10 years. And you are like in the lion's den, and you get asked this question, right? And I stupidly said, India. And all of my colleagues were looking at me, what's wrong with you, Raja? Right, we are here, and, all the stuff. What's that? And when the whole thing ended, we were leaving, he came up to me, and he said, "You're absolutely right." Right. And and at the end of my talk, I'll tell you what he said, why that was the case. Okay. So I am jet lagged. So I may say some stupid things again, right? So I apologize in advance. But there is this. I want to start my real talk with this statement. This is a gentleman named Rich Sutton, a pioneer in AI. When I talk about AI, it is, this statement I go by, right? He says the biggest lesson that can be read from the 70 years of AI research. There's lots of buzzwords, lots of stuff, lots of cool things everybody talks about, but he says the general, simple methods of computation are ultimately the most effective, right? Some call it brute force, right? That's because Moore's law made this general purpose computation cheaper, affordable, and all. And one theme that you see over the last, 60 years, 70 years of technology progress is this notion of democratization of compute or democratization of technology. When we made a lot of compute available to a lot of people, major disruptions happened, right? Things that we didn't imagine, right? If you look at the PC era, which I grew up in, when we got 1 billion people access to a PC, right, the whole internet happened. We didn't, right now we look backwards and call that the Web 1.0 era, right? That was the end of the PC era, right? It was Web 1.0. And we digitized everything we could. Right now you have access to so much information, as Dr. Shiva was talking about, 118 zettabytes. We networked everything we could, Web 1.0. And if you see, on the y-axis, I have the compute accessible to people. I know the display is not very good here, but it keeps going up, from a few kiloflops to megaflops to, teraflops. And when we got to the mobile and cloud era, between 2000, after 2000, right, we got everybody connected to mobile. Everything is connected to a cloud, right? And India did very well on the mobile side, right? And these numbers may be a little dated. We may be over 1 billion now, over 800 million smartphones, highest data consumption per user, lowest cost per bit. I'll come back a little later to show that India didn't do that well on cloud. Okay, we'll talk about that in a second. That's what happened. And now, so that's the past. What's the future, right? And this was the Web 2.0. Everyone talks about Web 3.0 now, right? I like to call it the distributed intelligence era, where there'll be over 1 trillion devices, trillion intelligent devices, by the time we get to 2030, right? Just imagine, right? From 1 billion PCs to 1 trillion intelligent devices, right? That is the market. That is what it's going. In fact, today, as we speak, there was a Google talk recently. They said there are 300 billion of this, right? No wonder we have supply chain crisis, right? All of them need silicon, okay? Now, the y-axis, see, it keeps going up. If you want the device to be intelligent, it needs lots of computing. The demand for AI computation, this whole deep learning, has been outpacing Moore's law, right? So every 3 to 4 months, the size of the network we can train and get something useful out has been doubling the compute demand on the y-axis. In fact, to train the most recent networks within the next 3-4 years, we need a zetta scale, the 10 to the power of 21, as Dr. Shiva said, all the stars in the universe level compute to train these neural nets, right? That is, the framing for zetta scale. Now, there are many, many reasons why you need more compute, okay? I decided not to go into the why aspect of compute today. You know, that's a whole another presentation. But trust me, we will all need a lot of compute. Access to compute is as basic as access to air, water, and other natural things that we all live by. And this compute is necessary from sensors to edge to data center. Why, right? We're generating, you know, Dr. Shiva said 118 zettabytes. We are on trajectory to 175 zettabytes over the next 5 years on instantaneous data that's being generated by users. You can't move all of this data from sensors to data center every millisecond. It's huge, humongous waste. You want to compute, you want to get the insights of the data where they're generated, throw the garbage away, and send the insight to where you want to store, right? And if you look at the computational capabilities today, we have sensors, right? I'd like to use like the neurons for the sensors, and I'll get to why that is. At the edge, we have teraflops, right? If you have an iPhone in your pocket, iPhone 13, it's a teraflop GPU inside that iPhone, okay? That's not a big number. It used to be a supercomputer 15 years ago, right? You know, size of this whole room that we are in here. Now, petaflops will be at the edge. I'll show it to you in a second. I think I have my petaflop thing sitting there. I'll show that in a second when I show the, yeah. So this is a petaflop GPU that I can hold in my palm, right? I'll show you what it's built on. And the data centers are going to exaflops, right? US is building 3 exascale supercomputers. So is China. So will Europe. Now, the demand for the AI compute, if you look at by 2025, we need at each of these places a 1,000x increase in compute. We need over 1 billion neuron capability. And now you look at billion neurons sounds big, but human brain is of the order of 100 billion neurons, right? So it's not that big to mimic a brain, but to do your basic surveillance, cameras or other edge equipment, you need that level of compute sitting at the edge. The left side of the edge needs petaflops, like I show, right? I used to joke, it was in 2016, I said, I'll have a petaflop computer in my Tesla, and everybody laughed at me, right? And they said, why do you need a petaflop computer in a Tesla? And today, if you go to San Francisco, all of the Waymo cars that drive around collecting data and doing the autonomous driving have a petascale computer sitting inside them in 2022. Edge will go exaflops and data centers will go zettaflops of AI compute. That's what we need to get to in 25. Now, it's not going to be easy to get to this, right? I mean, the demand exists, but the technology still has challenges. And that's the opportunity for India that I want to highlight, right? These numbers that I put on PowerPoint, the beautiful thing about PowerPoint is you can make up anything, right? It's just, you know, multiply by 1,000, put 3 numbers, and say by 2025, we get at a scale. Unfortunately, we haven't still invented a technology that can take PowerPoint and get a product out, right? Now, if you look at those numbers, okay, and now speaking of manufacturing, why Intel and Pat talks a lot about manufacturing. We are talking about over 1 trillion connected devices, or 1,000x more compute. And even if you assume perfect Moore's law is going on, doubling every 2 months, every 18 years, you need about 100x more wafer capacity than exists in the world today, right? About 100x more wafer capacity, okay? Whether that is in form of 100x more fabs or fabs that produce smaller number of fabs that produce more, that's what is needed. This is why we need to build the capacity everywhere. The rest of my talk will be about the full stack that we require. The semiconductor ecosystem, getting to zettascale, is not just about silicon. It is about silicon, systems, and software, right? And I use the word architecture. So, the most famous computer architecture book is from Patterson and Hennessy. In that book, in the first edition or something, they have this funny picture. This picture actually is stolen from that book, where they have this hardware guy, right, like a little grumpy-looking, unhappy person like Jim Keller yesterday, right? And then there is this ISA contract, right, instruction set x86 and all. And then there are these two happy dancing software guys up at the top, right? So that's the definition of architecture, is actually the hardware-software contract, right? And we still, think about architecture and hardware as this ISA, right? Is that there is an instruction set architecture, and now there's this whole momentum around RISC-V as an alternative to x86 and ARM. This is a pretty fine, simple abstraction. But the path to zettascale, right, is a bit more, let's say, not way more, a bit more complicated than this, okay? I like this picture. Remember this picture, right? A grumpy hardware dude and a couple of, fun software folks. The picture on the left is my favorite picture, right? It's the scale of numbers we deal with, okay? At the bottom, we have really small numbers, angstroms, 10 to the power of minus 10, right? And the top, really large numbers, 10 to the power of 21. That's the scale of computation we are creating. How do we tame these teeny little transistors? How do we put them all together in interesting ways, interesting architectures, packaging and all, to get to the zettascale, right? So that is not just, hey, let's get to a RISC-V scalar architecture and you get to zettascale. That is one teeny ingredient. So I took liberty to make a different version of the famous, Hennessy-Patterson cartoon, okay? There's still a little more happier hardware dude, think looks a little Indian here. And, I still have to deal with the instruction set architecture for scalar, but increasingly the action is at the system architecture, where you have to deal with power, memory, interconnect, and even more importantly, the accelerators. How are you going to integrate this high-density vector matrix neuromorphic computing? And then on top, you have software architecture. How do you abstract all this complicated system architecture in a simple manner to the software folks? And also some of the AI programming paradigms that Jim talked about yesterday. How do we get software folks trained on dealing with this AI thing? And that's my kind of the angstrom to zeta thing, that across this whole stack, India needs to participate, drive new innovations. And this space, entire from bottom to top, like the conversation with the Israeli Prime Minister, it is very early days. No one is ahead. So it is India's opportunity to grab this. Now, I said zettascale, right? So this year, there'll be a 2 exaflop machine in the United States, okay? So to get to zettascale, you need to get to 500x improvement, roughly, right? 500x. So we set at Intel targets, we call them moonshots, right? We said 5x improvement from process technology, the foundational silicon. 6x on top of that, right? So 5 times 6 will be 30 on advanced packaging, memory integration, photonics, power delivery, thermals. So we have teams working on all of this stuff, and this is an area, again, for us to collaborate with teams in India. And 16x in system architecture. And this is how we integrate other forms of computing with the scalar instruction set, whether it's RISC-V or x86. So that's how we broke up, and if somebody smart there is running the math here, it's only 480. We're still short that 20, right? So there's still some opportunities for ideas. And I'll give a quick flyby of what Intel's menu is, right? What we are working on, what our kind of public roadmaps are. The first is our process technology roadmap. This is kind of our most important thing. More than half the company works on it. Today, we are at that Intel 7 is our main production node. Next year, we have Intel 4. And in fact, we have some very high performance data center CPUs with high bandwidth memory being produced on Intel 7. And this chip that I'm holding, this Sapphire Rapids, built on Intel 7, it is the fastest data center chip today. And this is entirely designed. This chip is designed here in Bangalore. Okay? So the lead for the design team works here in Bangalore and all. So that's the state of the CPUs. Now, the second aspect that we work on, like we have in the audience, right, the godfather or the god or the guru of packaging, Professor Rao Tumala, right? So, I feel a little kind of awkward talking about packaging in front of him, but this is Intel's advanced packaging roadmap. For years, Intel had enormous investments and were leader in packaging. And one of the things about packaging is that if the bump pitch, the pitch you use to connect two chips together, as it gets smaller, you can run more bandwidth, and you can run it much more power efficiently at lower power and all. So when you see smaller numbers, small numbers are good. In general, I think for all transistor-related things, small is good. So today, the Sapphire Rapids that I shown is at the 55-micron bump pitch. The next one, the Foveros technology, where we stack 3D, we have done a product. This is Ponte Vecchio, which uses 3D stacking with Foveros technology, and that is this one. This is the world's most complex silicon right now. This is the world's most powerful chip. This is what is powering the US exascale computer. And over 100 billion transistors on this, 47 tiles, right? I mean, this is, people think I'm crazy because we haven't done 2 tiles before, right? I went from 2 to 47, okay? And this, 80% of the design of this is done between Bangalore and Hyderabad, okay? So world's fastest supercomputing chip is already designed and done in India, okay? So that's one thing to remember. Now, architectures, right? There is the CPU architectures. CPUs are really good at scalar processing. GPUs are really good at vector processing. Then there is this new thing for AI called TPUs coming. I call them matrix processors. And then there is this, there are probably another dozen of architectures beyond these 3. These 3 are kind of mainstays today. I picked neuromorphic for the async computing and its low power characteristics, and they're really good on sparsity. I think that last one is a bet. It could be anything. Who wins that other 4th architecture? I don't know at this point. But with this advanced packaging, we are able to do what's called hybrid computing architectures. We can combine, instead of before, it's like, hey, there is this CPU, there is this GPU. I can put elements of a CPU, a GPU, a TPU, and a NUPU, the neuromorphic stuff, on the same package in one chip and ship it to my customer, okay? Thanks to, pioneers like Professor Rao, we are able to do this in hardware. Okay, so the hardware aspect is kind of largely solved, I'd say, in the sense that we can do it. But there is a software problem. To just support one architecture, the x86 architecture, there are over 20 million developers on this architecture. It took us 30, 40 years to build the ecosystem for one architecture, from low-level software, firmware BIOS, drivers, operating system, developer tools and all. It took 20 plus years to support one architecture. So today's approach that you see is fragmented proprietary solutions for all these new architectures. Every startup comes and they say, I'm doing AI, and tries to build this entire stack that took 20 years. And guess what? All hardware, AI hardware startups, the successful ones, if there are any, they have been acquisitions by Intel. That's all. There's no other AI startup yet that is successful. The reason being software. They all have great, tremendous hardware. So we've been working, and especially as India thinks about RISC-V and all this stuff, this is a problem you need to tackle. If not, it'll be 10 years of work and nothing to show. Okay, there'll be nothing to show if we don't deal with this head-on. So what we have been doing at Intel, we started this effort called One API. Okay, so what One API is, we are taking each level, right, in the firmware level, we call it the level sub-zero, unify that level for all these architectures. And there is level 0, which is the operating system layer, unify everything in level 0. That is the level 0 API that we have architected. And then there's the level 1 API at the application level, so that you are abstracting the complexity of these hardware architectures away from the programmer, right? That's the key. And we are early in this journey, and I show you the progress, right? On the level 1, we are much further ahead. We got, scalar vector fully covered. It's open source. You can all download and use. And level 0 is, halfway through vector, and level sub-zero needs more progress. Now, the reason I'm putting this is a huge opportunity for Intel and India to collaborate, as India also invests in RISC-V and other architectures at the bottom of the stack. Because if you don't deal with this software problem, like I said earlier, it's a waste of time. Now, there is another software problem. There are two big software problems. Jim kind of hit on it yesterday. Now, programmers, and particularly a vast majority of programmers in India, right, use highly productive tools like Python and very high-level programming tools. What they achieve, so I can give them a zettaflop hardware. The performance they achieve will be at the bottom dot. The hardware entitlement is a zettaflop, but the actual performance they get on the zettaflop machine is this teeny little dot. Guess what? For some of there was a famous paper written by somebody at Google last year. It was called The Room at the Top. I have a question mark. Guess the order of magnitude delta between just a plain vanilla Python program and what's hardware capability is. It's over 63,000x, right? You take a Python program. Now you take that program and this particular gentleman, he moved from Python to Java, he got performance improvement. He moved from Java to C, more improvement. Then he introduced parallel loops, he got more improvement. And then a better parallel loop, more improvement. Then he vectorized it, more improvement. And then he put SIMD AVX512 instructions, and he got 65,000. From where he started, he got 65,000x. Now, how do we make this more automatic? That people, we don't want them to, train everybody to think this hardware and figure out all this low-level architecture details. We want, remember the first picture, software guys to have fun, right? Dancing, and the hardware guys to suffer, right? That's the right balance, by the way. And it shows my bias. I'm more software, and Jim is more hardware. So, software guys need to take more. So hardware needs to take more pain. So, the key elements. Just summarizing what I spoke, Intel and India Semiconductor mission, if we want to get Zeta-scale AI for India by 2027, in fact, like I said, I'd really like to do something by 2025. Right? 27 is, I think, a little late. On the software, one API for RISC-V is a huge collaboration opportunity. And productive AI programming, how do we cover this 63,000x gap? On the systems, there is excellent work going on RISC-V scalar. Professor Kamakoti and all are building the RISC-V CPU and many exciting efforts going on. We need RISC-V vector matrix sorted out for Zettascale. I've been talking about silicon photonics and some package integration work that we can do in India as well. That's a great, another great opportunity to collaborate. And on silicon, of course, right, manufacturing, process, packaging. I didn't want to go into that because I know that gets covered a lot. That gets more coverage. I didn't want to add to additional thing to that. So if you do all of this, right, this key technologies for Zettascale, let's come back to the question I started with. Who will be ahead in AI technology by 2030? India. Well, I'd say no. Okay? Well, everything I said is necessary, but not sufficient. Okay? Because I show you these pictures now. Okay? Now, these pictures show the number of servers, right? If India has one server, for every one data center server India has, there are 17 in China and there are 24 in the United States. There are a quarter of that in Israel. But if you now map it to per million people, okay, for million people, we are off, even relative to the tiny country Israel, right? You can do the math. By 40 times, and by over 100 factor versus United States. As Dr. Shiva said, right, building technology is not sufficient if you are not using it, right? And the other statement I'd make is that the people who built the best technology already have access to the best technology. For you to build the next best computer, you need access to the best computer of today. You need to be able to simulate your next computer. So India can't be a leader without being a leader in compute. So my ask is we aim for massively increasing the computational capability of India. I have this picture, 50 exascale computers spread all across India. Actually, each computer is a 20 exaflop one, and 50 times 20 would get you Zettascale, and they're all spread across 100-kilometer radius, because I can get sub-10 millisecond latency between these centers, and you can run entire India as if it was one computer, right? So this is the India that I dream of. This is the India that we should all dream of, and this Zettascale. India already has a name for Zettascale for thousands of years, by the way. So that we know how to deal with big numbers than any other civilization in the planet. And before I get to question, right? So my team got a little creative and made a little animation for the whole thing of the system, software, and silicon in India, inspired by the movie RRR. And the logo, so hope that plays here. Audio? So, questions? That's our poster, by the way. What? Oh, this one? overnight. Yeah, we have some very creative people. Yeah. You know, if I have to make it, it'll probably take a week, or or I have to go to YouTube and start learning everything I forgot.
Good morning. Very inspiring. The question I have is, for Intel to create the software stack, it's the same company. Whereas in India, the challenge will be the many different companies, startups coming and working in. How do you envisage that? Who is going to collect them together in one direction, where the one API or all these things are going to be?
Yeah.
It's a very, very difficult problem to solve at this time.
Yeah.
Unless we get into a regulatory, I don't know what is that, but can you throw some light on that?
Absolutely. First, great question. I didn't, in the interest of time, didn't get into that, but I will, because you asked the question. So, if you are inspired by RISC-V, right? So, how did RISC-V come about? Right, so you have a consortium, you have a specification, okay? We have a set of people contributing it. You want to add an instruction to RISC-V, right? There is a process to do that. Now, every layer of abstraction that I talked about, right? Sub-zero, spec. There is a spec for sub-zero. There is a spec for level 0. There is a spec for one API application stuff. So we want to treat those like RISC-V, right? So give them, clean names and all. And everybody that is working in this ecosystem needs to get onto those specifications and implement their layers to those standards, okay? And just like with RISC-V, we got incentivized. We are incentivizing, actually Intel, spends a lot of effort on incentivizing one API. We made it open source so that it works on our competitors' hardware and all, but and I recently actually got it working on ARM, by the way, right? With the collaboration with Cyperl in Europe. We haven't yet done anything about RISC-V, okay? So this is an opportunity to define a consortium, a standards body around software as well, like we're doing for RISC-V. And, we can come up with some creative name and drive it. And like I said, India could be the center that drives this software standardization for heterogeneity. Thank you.
Jai Hind, Raja. I think this is for bringing out you from the jet lag. Actually, thanks for the setting up a new goal for the software industry in India for the AI technology by 2030. But we are good in S first, but S square we would like to go, silicon and system. This is what the vision of our new government, and of course, with this, what conference is going on is focus on the hardware building. We would be happy if design is being done here, and of course next chip will be fabricated in India and system assembly will be. This is the goal of this one. I would like to ask how Intel can support Indian manufacturing facilities in future. So Intel is also going for Indian Intel Foundry services. If India build a semiconductor facilities, how Intel can useful to load the fabs or translating the IP which are being generated here, or of course owned by you and being fabricated there, and they can be loaded here in India again, number one. Number two, what are the nodes for initial startup for the fabs in India should be focused by India? Thank you. And Jai Hind.
Thank you. Thank you. Good question. There's one thing I'd like to say, though. There is a perception that India is strong on software, okay, which is kind of true for that super upper levels of the stack, okay. The middle, I actually cut that part of my presentation. I actually go into lots of gory details on the system software stack that sits in between, like, the people having fun about in this stuff. We aren't that strong. In fact, that's one of my biggest challenges in India is getting the software people close to hardware, understand how architectures work, and dealing at the ISA level, okay? So first thing, I think we got to train, we got to get that mindset that people need to get to that low-level detail. In terms of manufacturing, like I said, one thing that became clear to me over the past year plus is it's not a question of if India will get manufacturing, whether it's from Intel and other folks, when. it's inevitable. If you have to get 100x more capacity, if you want to get capacity close to consumption, the whole supply chain stuff, it is inevitable. It is just going to happen, okay? So, I can't predict exactly, is it 5 years we'll have the world's most advanced silicon fab or not. Now, there is so much more than producing transistors. That's one of the things I know, it was a very short talk I was trying to get, is that the way these systems are built, from the transistor wafer coming out to actually something in your hand, there is so much more hardware packaging work and manufacturing work that happens. I think India can leapfrog and take that on much sooner than waiting for an angstrom process technology showing up here. Even the fabs that we are building, the new ones in Europe and all, they'll be like 5 years, 6 years before the first wafer comes out. I don't think you want to wait. The energy that I saw in India, this trip and my last trip when I went to New Delhi, it's like amazing. We shouldn't wait for 5 years. We should figure out what we're doing in 23, 24, 25, 26, have goals across all this and go execute, right? Thank you.
So I'm grateful that you brought this attention to the systems part and the middleware that we are, let's say, not as strong as other parts of the world. And assuming that that is our focus and that we want to create an ecosystem of startups and catalyze that ecosystem that is focusing on system design innovation and the middleware, what suggestions do you have in terms of what we should do as government to create some real momentum there? And because that is clearly in our mind, that is a missing piece. We want to expand that. We've done some pieces, as you know, with the DIR5. And what else do you think we should be doing?
Yeah, I think there are, there are a laundry list of things, but the simplest thing I'd say is that every business, small, big, all sizes, should be encouraged to build their on-prem computing. Like, I was in Hyderabad, watched a relatively small silicon company build their own data center. I was, filled with joy seeing that, oh, you can actually build this in India, or did you just kind of get it? No, he walked through what they did and all. I said, that encouraging everybody, every silicon design company, if you build your infrastructure in India, okay, the data center, the location, some incentives, whether it is power or tariffs of the equipment that they have to buy, if you are hosting your data center in India, you get an advantage, right? The government actually encourages you, just like you're doing with auto manufacturing and all, is the simplest thing that I can suggest, right? Silicon design, by the way, uses a lot of data center infrastructure computing. In fact, so much so that that chip that I'm holding, the 100 billion transistor, Intel, which spends billions of dollars, by the way, okay, billions of dollars in the infrastructure, we didn't have enough compute to simulate that entire chip. So it is we took 1/16th size of the chip to run on an emulation and hope to God that when the chip comes out, it'll work, right? Because I couldn't do the whole simulation before the tape out. So and as you're encouraging more design in India, the compute needs for those designs will also increase. And today they all go to North America, or like the data centers are everywhere, that even though I have the huge design team in Bangalore, it pains me that they run their simulations in data center that sits in Santa Clara.
Why not?
I think I would like to touch on this one API, this thing. I think I really love this because standardization is the key for, ecosystem working together, and particularly in large nation like India, and we have plethora of startups. But the problem that whenever we talk about standardization, the startups have a very simple argument. Standards block innovation, and they try to get away with that. And while everybody knows without that you cannot work together, there's no interoperability, and particularly this level of sub-zero level, one API is one of the most crucial one. Without that, nothing, upper layers will never be able to build. What do you think? How do we now proliferate this respect for standardization, working collaboratively together rather than my shade of green, my shade of blue.
Yeah, no, I think Jim kind of touched on this yesterday, right? It's inevitable, especially when you have a booming startup ecosystem and all, that people will go off, like, and dig their own holes, I call it, right? And then 5 years later realize that, oh, I should have listened to, this guy with gray hair, right? And, followed the standard and all. I wasted a lot of time building this stuff that my value is someplace else, right? So that inevitably happens. But in that process, they also discover something that end up contributing to the standard, right? They discover, hey, you didn't have this particular feature in your standard that I'm getting like 20x speed up if I can, express a particular operation with a particular API. So I think it's that churn, right? It's like, right, creation happens. Great things get created when there is a when there is a churn, right? That's our entire Kshirasagara Madanam, right? that entire churn. You want creation, there is a churn. Startup ecosystem means churn, right? And we, as people who have scars on our back, need to help them, right? Need to help them through that churn.
Sure. Thanks.
So,
One more? May I?
so my name is Ashutosh. So my mind is still stuck to the question, why in the meeting with the Prime Minister Netanyahu, why did you say India would be ahead by 2030?
Oh, yeah. Like I said, I was serious. I wasn't thinking, okay? I wasn't thinking. But he came to me and said, yeah, thanks for reminding me. He said, and I later learned that he's actually, Mr. Netanyahu studies world history. I think he got, one of his degrees from MIT was in world history. He has 3 or 4, degrees. He said the two cultures that have the thing he told me was the two cultures that have the breadth and depth, to deal with, to tackle with problems of this size. And the culture, he said, culture gets built over thousands of generations, and India got it, and India got scale larger than Israel. So you're right. People talk about China. He said people are worried about China being in this stuff. He said, India got the cultural depth and breadth, was what he said. Thank you. Oh, yeah.
I think 30 years back, right, our fearless leader, Gordon Moore, right? I say ours because Intel Run is still in me. Made things very simple by making the Moore's law, right? Everybody understood very easily, 18 months, 1.5. Now this with all terminology of Intel 7, TSMC 5, I think it's getting very confusing. What is the reason for Intel to make things so complicated now to understand what node is what, right?
Yeah, so by the way, people say Moore's law, like, Gordon woke up and, came down the mountain and profused this stuff and all. Actually, if anyone has a calculator, okay, do 1.01 to the power of 72. Okay? 1.01 to the power of 72 is actually the Moore's law. That is 2x. Okay? 72 is 72 weeks. Okay? So if you pick any problem, and you persist on the problem, and you set a goal of an average 1% improvement. By the way, this applies to goals in your life as well, right? Just 1%. 1% sounds easy, right? It's like, yeah, I'm 200 pounds and 1%, can I lose 0.5 pounds every week, right? If I'm disciplined and if my scale collaborates, seems easy, right? It compounds. Moore's law is compounding, law, and The issue is, actually, we are off Moore's law a long time ago, the whole industry, right? Because the iteration time during Gordon's time, in a week, you run an experiment, in a week you got the result of that experiment, and you set yourself up for the next week, okay? Now it's a 3-month cycle. That's my fastest loop is 3 months on the advanced process technology. So now you run, 3 months is how many weeks, right? 12 weeks, right? So real Moore's law is running over 5-year cycle. Okay, so now we've been a little faking the Moore's law by starting 5 years ahead, right? And running multiple process lines and all. And people who figured that out early, like our friends in Taiwan, have been doing this for a little while, especially, in the transition to FinFET and all. And when they noticed the complexity of the stack has increased, okay? And that's the power of open ecosystem, by the way, right? Because they got scale, they are able to afford to be able to run multiple teams in parallel, right? If you're one design, right, and you're stuck behind a serial process, you can't run the parallel stuff, right? So things get... Oh, yeah. No, I'm saying that, so then there is the node marketing. TSMC does marketing, Intel does marketing, and, the node names, what is a nanometer, right, in the metal stack got very confusing, right? You got each transistor that we produce is a combination of multiple nanometers, right? And I have Pushkar in the audience here. He's, the semiconductor physics expert. He can go into the gory details of that. So, the marketing, people are used to one simple name and all that stuff. So, the nomenclature is very confusing. That's why we switched to the angstrom nomenclature from nanometer, because, now it's less than 1, and you can't call it 0.1 nanometer and all that stuff. So, I think that's another conversation.
Sorry. The next, sorry about that, because it's already 15 minutes late, and we have other speakers already ready on the virtual mode. Sorry for that. I'd like to straight away go over to the fireside chat on silicon-driven AI ML revolution. Can you hear us, sir?
Yes, we can.
Yeah, please go ahead. Yeah.
Okay. So let me kind of set the stage, and then maybe I'll let Wally and Sid kind of chime in. Share a few slides here, if you don't mind. Because we look at, while Raja's talk is exciting, it's pretty much at the leading edge of the technology curve. And I'd like to talk a little bit about where the growth in semiconductors is actually going to be over the next several years. Hope you can see this slide that I'm sharing with you. Just give me a minute, and I'll be with you. Share, where did share go? Here we go. Okay. Okay, can you see the slides?
Yes.
Okay. So if you look at it, right, the growth for semiconductors related to artificial intelligence is expected to actually be 5 times greater than the growth in the remainder of the market. And although it's coming off a very small base, we expect there's going to be a tremendous amount of opportunities for companies that are competing in this area, right? As a matter of fact today, India's AI market, based on IDC study, is expected to reach about $7.8 billion by 2025. And interestingly enough, there's a study done by McKinsey which talks about what happens across the regions. The AI adoption rate is actually highest at the Indian companies, right? And a large part of this was the approach that the Indian government took with the Digital India standard that was driven down. And the 4 major areas that there's been a good bit of focus on was one on schools, second on healthcare, primarily related more to the IT side of things. And I'll talk a little bit more later during this presentation about why edge AI and endpoint AI is probably far more interesting than actually focusing on the cloud aspects of it alone. The other side is the aviation industry is sort of focused on fleet management. And then the customer experience side, where the customer sentiment and things of that nature are being measured, right? So those are the important elements of what's driving growth. But let me just move to the next slide, which is actually far more interesting from my perspective. I wonder why this is not moving to the next slide. Okay, I went too far down the line. Okay, so if you look at this now, right, and you look at the AI market dynamics, intelligence is actually moving much more towards the edge. While the core and the data center will continue to be important, which is primarily focused on training algorithms, the inferencing becomes a 10x over training algorithms when it comes to importance. And interestingly enough, the power domain is not towards the high power side, but at the sub 5 watt power domain. That's where most of the growth is actually going to occur in this space. And further, right, the edge is going to be more than 2.5 times the growth on the enterprise side of the business. So typically when you talk about edge AI or endpoint AI, it's really about embedded applications applying a pre-trained model to a specific task. That's the generic use case. And I kind of wanted to set the stage on what's happening in the AI world. And I'll kind of turn it over to Wally and Sid to talk a little bit more about their respective views on the subject. So Wally, do you want to take over?
Okay, I've become deeply involved in this part of the market in recent times through our company. And let me see if I can, you'll have to stop sharing.
I'll stop sharing, yep. Done, yep, there you go, Wally.
Okay, see if I can get on here. When last time I spoke in India, I was still CEO of Mentor Graphics, which had become Siemens EDA, and I was doing some work for the design for the defense, or for DARPA for the U.S. And they asked me to look into fully homomorphic encryption, and I did. I surveyed all the companies that would be involved, because the U.S. has correctly concluded that with quantum computing, once we get past 1,000 qubits, essentially all of the security on the internet can be broken. So we have to move to the next stage, and that next stage already has been designated will be fully homomorphic encryption. But all of the companies I talked to said this is decades away. Because it requires so much computation. And it was then that I ran into an old friend, Gordy Campbell, founder of Chips and Technologies and 3DFX and Soft Machines and others. And Gordy was working on a software company that had developed compiler technology to compile applications into totally independent streams of control and data. And that company was called Kornami, for a tsunami of cores. And the reason was that after 7 years of development of the software, they found that traditional von Neumann architectures cannot run independently. And so the whole problem of parallelism with multiple cores is there's too much interdependence, there's shared memory, there's synchronization. You have to have totally independent streams of control and data. So Kornami, after 7 years of developing compiler software, then decided to develop a chip and then a compute fabric where you connect multiple chips together, multiple servers, and achieve performance that's linearly scalable with the number of cores. And that's what Kornami does. Now, of course, you can use this for machine learning, artificial intelligence, particularly good for inferencing and getting orders of magnitude higher performance than what we achieve today with NVIDIA servers. But if you want to really change the world, you do something like fully homomorphic encryption, which then changes every server in the world, because at the same cost, if you want secure information versus insecure, why wouldn't you take the secure? And the way it impacts machine learning, among other things, is that you can take encrypted data and build machine learning models without ever decrypting the data. So people are very concerned about their medical data or other things, and they're able to, they don't have to ever disclose it. It can be maintained in encrypted form. You make encrypted queries to an encrypted model and get encrypted results. No one ever sees the actual data. And so fully homomorphic encryption, I believe, will revolutionize the world. The client has his or her data, they encrypt it, send it to the cloud. Processing is done while it remains encrypted. No one has a key, no one ever sees the plain text data, and the results are sent back in encrypted form. And so the part that I'm involved in, similar to the kinds of things you're working on, is based on doing a chip to implement that software, a chip that's made up of dynamically programmable cores, which can be put together and dynamically reconfigured under software, and which can then be put together in chips, boards, and servers, and provide performance that is orders of magnitude greater than what you could get with an NVIDIA server or Intel processors, and take us to the next level of compute, the next level of machine learning inference and capability. And it's something that's not years away. It's something that's very close.
Sid?
Yeah, thank you. I think this is great to, first of all, be here and the opportunity that has been given to D-Matrix to present. What I thought is I'll share a few slides, and I'm glad to see this emphasis on inference today, because that is exactly what we are doing. And I totally agree with how Sailesh started out the panel when he said, how do you build a computing platform that can scale from cloud to edge, because workloads are over time going to transition away from the cloud to the edge. So let me share a few slides here and tell you a little bit about what we are doing at D-Matrix. And let me know when you can see these. So yeah, I mean, we are a relatively newer company compared to obviously Renesas, and allowed to speak with you. But the core innovation at D-Matrix is really something that we call in-memory compute. And in-memory compute is something that is very, very well suited for inferencing applications, specifically matrix math acceleration. When people talk about in-memory compute, there's different flavors of in-memory compute. What we are doing is we are building an SRAM-based in-memory computing engine. So this is on-chip in-memory compute. It is fully digital. Again, the tendency when people think of in-memory is that there is some level of mixed signal analog compute involved. This is a truly digital engine, and it is as accurate as a traditional digital accelerator. So what we have really done is marry the accuracy and predictability of digital compute with the efficiency of in-memory compute, and we call this a digital in-memory computing engine. And it really kind of helps us break through what we call the AI barrier, or how do we kind of co-locate compute and memory, and that's how we get a massive boost in efficiency to do data center inference. The other thing that a lot of you folks who are following what's happening with AI workloads specifically, transformers are essentially taking over the world, right? Transformers was a workload that was invented by Google researchers in 2017. They published that research. It was initially targeted for natural language processing and understanding. Since then, this stuff has essentially taken over a lot of different applications, from search to content moderation to conversational AI agents, document processing, et cetera, and it is expected to take over vision and video. So the first 4 years of AI compute was a lot about convolutional AI, but now we are moving into the age of transformer AI. And at D-Matrix, we are really building a clean slate computing platform targeted for transformer AI, because that is really going to be with us for the next 5 to 10 years. And really, that's where most of the compute emphasis is going to be. And in terms of, I'm sure you've heard a lot about chiplets at the conference. You've heard a lot about open source. And this is where I'd like to touch upon the theme that Sailesh originally started with, is how do you build something that can transcend all the way from cloud data centers all the way to edge data centers, and even into micro edge data centers, potentially client compute, right? And chiplet-based computing platforms really offer you that flexibility, which is what we are doing at D-Matrix. Really, we don't believe in building massive, big chips that really need to be fit into a single application, but really building smaller chips, building a fabric of those chips. And you can really scale these. You can build solutions with 1 chiplet, 2 chiplets, 4 chiplets, 8 chiplets, and depending on the need of the application, you can do both scale up and scale out. And you can really go after multiple different markets, whether it's edge or cloud, depending on the compute needs of the application. So that is how we are approaching the problem at D-Matrix, all the way from IP to chiplets to cards to systems. and really kind of giving us that flexibility, modularity, and scalability across applications. But with that, turn it back to Sailesh, and we can take more questions or continue the dialogue.
Yeah. So let me share one more slide here from my piece of it, if I can. And I just want to set the stage for the teams that are listening in, because the interesting thing in this arena, right, is people focus primarily, if you will, on the training algorithm side of the business. And actually, if you look at it, some of the biggest opportunities that lie in India are in other verticals. They are in smart home, in things like healthcare, in things like industrial automation, building automation, and energy management, right? And I'll give you a very simple couple of very simple statistics which are very relevant when it comes to the healthcare sector. Like 1 in 11 Indians, for example, right, suffers from diabetes. 30% suffer from hypertension, 45 million from heart problems, and stunningly, right, 10% of the respiratory deaths are chronic because of pollution problems that occur there. And deaths are some of the biggest challenges. So if you think about how sensors and AI can help, there is technologies out there today that can detect the advent of a cardiac problem before it occurs. There are solutions out there today that you can use for blood pressure patches and so on that rely on AI technology for basically making a difference to people's quality of life. Other area that's hugely important for India, for example, is things like traffic fatalities, right? In 2019, there were close to 151,000 traffic fatalities that occur. But if you think about the advent of what's happening on autonomous vehicles and ADAS systems, that's an example of what's happening on the edge AI front that is making a difference in people's lives. Same thing when it comes to air quality, right? 63 out of the 100 cities in India were amongst the most polluted when it came to air quality. And again, with things like PM 2.5 monitoring, soil monitoring, all these are things that can be remotely tackled, and using AI have the ability to attack the problem at hand. And I'll leave you with one more thought before I turn it back to the panel here again. When you think about the complexity of voice recognition, with 1.3 billion people that India has, right, and 22 plus different languages, when you compare it with the capabilities that we should be having on that front versus China, we really have some room to go for improvement in that particular area. So I just want to seed some thoughts in the kinds of things that India should be thinking about on the AI perspective as we move forward. And I'll turn it back over to my panel here for any further comments, and then we'll open it up for questions. Wally?
Yeah, I would just like to add one comment, Sailesh. I mean, I would totally agree with that, right? I mean, the sensor data and the amount of information that is collected by end sensor nodes, right, is eventually going to need to be processed, right? And how close can you bring AI to the endpoints, right? And I think there is just a lot of silicon innovation that is going on in different areas that will allow for silicon to move closer and closer, or AI specifically to move closer, AI algorithms, AI compute to move closer and closer to the end nodes. This is something that has been missing. You know, as you said, most of the processing has been happening in the cloud. It is going to be impossible to take all these multitude of endpoints and feed all that information into the cloud and then process it there, bring it back. Inferencing specifically does not need to be done that way. So, you know, clearly over time, we see that processing moving closer to the endpoints, and how close to the endpoints can we go for more and more efficient processing is really something that is happening, and we are very excited about that.
So to Sid's point, moving to the edge becomes a critical part of all of the inferencing technology. One thing I find very interesting is that in the large investment that's been made in machine learning models, the protection of those models, the protection of the data has been minimal and has caused big problems. Tesla, for example, developed a very expensive machine learning model, which was then copied by their competitors. And if you look at the edge, to encrypt a machine learning model for automotive capabilities, it seems ridiculous because it has to run in real time. So how can you encrypt it and put the burden of that decryption? But if you could improve the performance by orders of magnitude, then you could have encrypted models. And if you can encrypt those models, then you can protect the value of the model you created. And if you can run at a sufficient speed, then you can run those models in encrypted form. And that's a big step forward from where we are today, and a capability that would then enormously increase the value of information, the ability of people who have information, who have valuable models, to protect those models so that others can get the benefit of using the models without ever seeing the plain text data.
No, I mean, actually, yeah, that's a pretty good point. And I mean, I think the opportunities, people focus so much on the training side of it, right, that they often forget what's happening on the other end, which is equally critical in terms of what's going on. So,
yeah, you train once, but you infer, n number of times, right?
Exactly. And I think as you know, if there was, I would say the one thing that from an India perspective, certainly Renaissance is investing quite a bit, and I'd be remiss if I didn't say we weren't doing that in India. We are growing our presence in Bangalore. We're partnered with Tata Elxsi for our next generation electric vehicle development. And there's multiple partnerships, especially from an IDH perspective, that we're working, because a lot of this sort of AI is application dependent. So if you don't have the ability to partner with somebody on the application front, you have your own set of challenges in terms of what happens there. So certainly we're doing a lot of that, but the opportunity in India is mostly, I would say, India should be thinking more about edge computing more than it does about the previous sets. I certainly think the data center presence will help, the server presence will help, but given the limitations on power, something to consider would be more along the lines of edge computing and what we can be done on that front. So.
Yeah, sorry for the intervention. The next 5 minutes you need to conclude the fireside chat. Yeah, 5 minutes.
I mean, go ahead. I'll open it up to my panel. I don't want to be hogging up all the time.
I think if I may add a point here, I think there's one area that India can really make a big difference in the growth of AI and really as AI permeates through different applications, and we touched upon different applications. Really, the software. Software is as big a piece of AI compute as the hardware, right? So yes, this is a panel on silicon innovation, and there has been a lot of silicon innovation, has played a massive role in the proliferation of AI over the last 8 to 10 years. Really, the big bang of AI, as they call it, happened in 2012 with AlexNet, which was an image detection model, a computer vision model, right? And then after that, there has been a set of improvements. Hardware has improved, software has improved, but now it is time to really deploy this stuff. We go back to inference. Right, you can train all these models all you want, but it is time to deploy these models, monetize them, find use cases, applications, and that's where really software plays a very big role. There's so many different vertical applications. We touched upon many of those in the beginning of the panel, but how do you really take the information, make sure that it is used and monetized in an intelligent fashion based on the decisions that the hardware is making, is really where the software comes in, and making sure that it is easy to use. Users can really take the information, do something with it. A lot of the end user interfaces are really tied to the software. So I think India can really play a very big role in terms of making the software really user friendly for the target applications and the end users.
So I'd say we'd welcome questions from the audience. It's really refreshing. I see Satya Gupta, I see Ajit Manoka, all these people, we all haven't gotten together for so long. It's so great to all be back in a single conference. I hope the rest of us can join in the near future.
So we'd like to open it up for questions, if there are any.
Yeah, there's a question. There's a question. It's coming right away.
Hi, Wali. No question, but glad to see you and Sid and Salesh. Really, I wish you were here in person and you would have really enjoyed the energy on the Semicon India 2022. But Wali, I was really impressed with the use of homomorphic encryption. So SEMI has been working actively with RBI to develop this data transfer model with encrypted homomorphic encryption. And I was intrigued with the amount of compute it needs. So when will it become practical that when we can easily transfer data without fear of somebody abusing the data? Any thoughts on that?
Yeah, so I think most people had felt that this was a long way away. I think it's going to happen very quickly. It'll happen with our company. It's going to happen from some other companies too. In order to run a computation on homomorphically encrypted data at the same rate as you would on plain text data, if you have the full range of computation, it's about 5 or 6 orders of magnitude performance. A single bit of information is encrypted into a 500-order polynomial with 64-bit floating point coefficients, and then to perform a logical operation requires thousands of fast Fourier transforms. That's a lot of computation. But the amazing part is there are at least half a dozen companies that believe they will add orders of magnitude to the performance, and we at Konami think we can solve the whole problem, certainly in the fairly near future, and then offer an alternative which is truly secure computing and which causes a really revolutionary change in the way data centers are managed, the way people do compute, the way data is protected, and the way data is sold and distributed, which I think will be very revolutionary.
Very good. I think in the interest of time, I want to invite 3 of you to Semicon West in July and have a follow-up discussion on this. Thank you very much.
I will be there, Ajit. I'm planning to go. Thanks very much.
Thank you.
Yeah, thank you very much. With this, we come to the end of this. We have a fireside chat. It's a combo of, it's a hybrid fireside chat, physically as well as virtually. Physically, we have Shri Barun Datta from IMEC to kindly come over. Mr. Barun. Yeah, kindly come over. He's the chief scientist of IMEC Leuven, Belgium. Let's give a round of applause for Mr. Barun. And he leads and has led various R&D programs across the IMEC semiconductor R&D ecosystem. And the fireside chat will be with Sajeev Dalal, the Executive Vice President, Business Management, and is responsible for focusing and directing the TSMC's business development and sales strategy. So, Mr. Barun, Mr. Sajeev is also ready. It's over to you. Yeah.
Hello, everybody. I guess this is going to be a slightly difficult session because we are following 3 great previous talks, and they've essentially taken everything we had to say. So Sajeev and I are going to improvise on the fly and try to do this as well as we can. Sajeev has been a long-term supporter of, through TSMC, of many of my fabulous initiatives, and TSMC and IMEC still have a very strong collaboration in promoting access to foundry services to all the SMEs and basically research institutes. That's something which is active, was started a long time ago in Europe, but has been very also recently more active in India. Sajeev has worked quite closely. And what we actually discussed a little bit, Sajeev, we'll have to, as we discussed, we'll have to improvise. So the best way I'm going to run this is, I will try to ask Sajeev a question, because Sajeev representing or knows the entire foundry ecosystem for the last, I don't know when. Sajeev and I go back, I think, to the early 2000s or even late 1990s. So we basically have been together for a long time. So knows the ecosystem very well, and he's been looking at emerging business for a long time.
So Mr. Datta, sorry for the intervention. Somebody has lost their right bracelet, a golden bracelet. So that's the reason, since it's a gold, this one. So if you have lost it, you need to identify. And Hema is here at the reception. Please check if any of you are wearing a gold bracelet. And amidst the semiconductor, there is a little bit of gold coming in now. So, right, but it's a lost one. So I'm sure the owner will get it. Yeah, back to you, sir.
So the session was titled Global Growth Drivers for the Foundry Ecosystem. So what I'm going to try to do is ask Sajeev a few questions and let him respond. And then I'll try to comment on them. And hopefully my comment is going to be intelligent and differentiated in what Sajeev says. So Sajeev, one of the things that you've been in this and have been focusing on the emerging markets or emerging new areas for Foundry. From your perspective, what are still the key drivers for growth of this business going forward? I think we've all looked at the mobile and everything else over the last couple of years, but going forward in the Indian ecosystem, to give people a perspective, what do you think is something that you see as standing out? Or what is it that you think you should be chasing?
Well, okay, so let's talk about it in two parts. The first part is the applications. The second part is sort of the technology trends that we see at TSMC. And I'll say that it's both for the major accounts as well as the startups driving innovation. So if you look at clearly digital transformation has come hard, accelerated everything. It's number of devices, content per devices. You've heard all of that, of course, over the course of yesterday and today. And it's been great, actually. This opportunity is great. I should start with that because it's not often that I see Siva and Raja and Sailesh in the same morning or in my evening. So I want to say, first of all, thank you for the opportunity. And okay, so let's get back again to, what's driving TAM and content growth? What do we see at TSMC? Of course, everybody's talked about HPC, the 5G, 6G trends, IoT. But other emerging areas are also extremely important. We see a lot of activity in healthcare that is going to keep driving business forward. It's a great time to be in semiconductors. So now let's just talk just 1 second on a few minutes on the technology trends. Clearly, I think Raja talked about computing, energy, efficient computing is driving things forward. The whole chiplet, and that represents a opportunity for India as well. Because as Raja talked about, there is 47 tiles. Not all tiles are made by the same company. There's a lot of mix and match. So again, there's an opportunity to be part of the tiles being made. There's high bandwidth, there's low power connectivity. But here's the most important thing I see, Varun, to go back to what you asked, which is, what are the opportunities for India? Well, if you look at the growth, it's not only the technologies that follow Moore's law. Every cell phone today requires power management devices. And there's my friends at Qualcomm can talk about how it's gone from 1 PMIC to 20 PMICs and even more. But if you look at where the silicon content is outpacing the capacity available, that's in mainstream technologies. And that's 28 nanometer and above. So again, a tremendous opportunity for India to think about, you don't have to follow Moore's law down that path. That's an expensive path. But there's a lot of other opportunities that are driven by technology trends. So, Varun, how do you see it from your end?
Yeah, so let me give you a little bit of insight. When I returned in 2010 to IMEC, IMEC till then was very much focused on supporting only, I would say, quite singularly, the Moore's law activities in R&D. And I was crazy enough at that time to say that I'm going to spend at least 30% of my time on non-scaling technologies. I kicked off a gallium nitride program to go take it to 200 millimeter. I kicked off a program in imaging. I kicked off one of the earliest programs in trying to use silicon platform for genomics, and a program in neurotech. And believe it or not, they have actually grown faster than I ever thought in size, with a completely different set of customer base. They're much more application-driven customers. They're not really silicon folks. But translating from that, I got close to the automotive industry in Europe. And one of the things that I learned from that is that my personal belief looking at it in the India context, because I think mobility, I don't like to talk about automotive, I like to talk about mobility, because automotive only thinks of cars, but there are, living in the Benelux, what I've realized is my major mode of transportation has changed from a car to a bicycle. Okay, you can say I've gone back 100 years, but it happens to be an electric bike, okay, which costs 8,000 euros, so it's not cheap. And this has got actually one of the strongest bases of gallium nitride power electronics. Infineon dominates in the supply of that. And to me, what is amazing is mobility, I think, is an option, and mobility applications are a huge opportunity, okay? And there is a local application source. The other important thing is, I think globally, we are pretty close to hitting the limits of total energy consumption. Okay, and you can figure out whether it's whether it's going to peak in the next 5 years or it's going to peak in the next 10 years, but we're getting close to it. So any thought of what I would say power management and conservation, okay, and the way I see it is that every single plug socket will have to become intelligent. Okay, and when I say this, when I say intelligent, it could be autonomous, it could be networked, but it'll have to be intelligence, and that is a huge amount of silicon. Okay, and it's quite likely that that won't be at anything more than 28 or might be 16 at the most, and most likely will need for power conversion and everything, even bigger nodes running up to 40 or 65. So I do think that we shouldn't, my expectation is, in the automotive side, is that I wouldn't be surprised if there is 3x more total wafer consumption in automotive than we have today. And similarly, in the energy conservation side, or what I would call industrial electronics side. And I think these are quite application specific and localized, because every application in this thing is also a huge source for entrepreneurship. Okay? My good friends at Samsara, who have built a platform, are trying to integrate all sorts of sensors, and the challenges they have locally is just massive. So I think this is a huge driver for silicon. I think we sometimes don't look at it because, or in fact, I like the fact that the previous speakers talked about inference at the edge. I think inference on the edge is not taken as seriously because that's where the sensor is going to be or the controller is going to be. Okay? So I think this is something which could be pleasantly be much bigger than we think it is today. Today, this whole market, it's true that the two biggest analog and linear product companies in the world, that's Texas Instruments and ADI, are the two most profitable semiconductor companies in the world. They're running at gross margins running at close to 70%. But they together are 40 billion in size, of 35 billion in size. But I think that market somehow has the potential to be a hidden growth driver. That I think is something we should not ignore. So having made that comment, I would move on to talking about what do you think about the design ecosystem driving foundry? What do you see as the needs or drivers coming from that side?
Yeah, good question, Barun. I'll actually tell you a personal story. So I think Satya Gupta in the room or Venkat from Mastership will know, 15 years ago, I actually visited India I led a team to see what the semiconductor landscape was. Wrote a report, went up to Morris Chang in Riksai, who was the CEO at that time, and said, I want to open an office in India. And we did. And the idea was to support the growing ecosystem of designers. And we opened an office in Bangalore, and I'll tell you, perhaps it was 15 years too early. Today, when I listen to everything that's being said, the dynamism, the excitement, I think it's from a TSMC perspective, I've got to go look at that again. But to answer the question, yes, we see that. The number of tape outs that come directly into Taiwan from India has gone up exponentially. It used to be 10 years ago, they would come through the multinational, just be, all the work was done in India. It would simply be branded as coming from the multinational as a tape out. Today, it comes directly. And that is such a promising sign of things to come. I know everybody's talked about having 20% of the workforce, but I think in terms of the design ecosystem, I'd say one thing that's important for India to do, and that is local products. As we drive consumption, we've got to look beyond just the consumption part of it. Where are the local products that address the local needs? I think I'll just speak from a fab perspective or a TSMC perspective. It's been all about the customer, satisfying the customer. We follow the customer. If there is the local need, then fabs make absolute sense. So I think strengthening the design ecosystem, sort of get them, the change of thinking is, we do service and we do service well. How about designing for our own products? So that's one thing. Now what does that require? Of course, that requires our, innovation, our startups. How do we support the startups? So I'm very encouraged to hear about how we support the startups. Of course, they need dollars, training. Now, I think, Barun, you and I talked about that we have been entrepreneurial by nature, right? I mean, a lot of us left India with 2 suitcases and $20 in our pockets and made our lives. So there is, just building on that trend, there is absolutely no reason why we couldn't have multiple startups driving semiconductor innovation. And then I think the manufacturing will come.
Right. I think just to counter that, I think sometimes we underestimate that today we still have to transit in India from thinking about marketplaces and services to a product engineering culture. And this is it's not such an easy thing, because the step up to product engineering is much more challenging. And I don't think it's a question of intellect. It's a question of attitude and culture, okay? And I think this is a place where the type of coursework even we do in university, and I'll give you an example, a small example. What differentiates the coursework in some of the top schools in the US and in Europe in, let's say, analog design, is they actually not only try to do a PLL or an op-amp, but they tape it out and it gets back from the fab. And Sajeev knows this because they provide support in getting these 0.18 micron tiny ASICs back to the pair of 2 students, but they actually sit down and measure it. And this changes and builds a certain level of product confidence, which I think is absolutely essential. Okay? I think most of us who have been in the US and grown up in the US and grown up through the engineering stream have been product builders. And that's why we land up in startups, and especially the silicon people. Okay? Might be a little less in the folks who went and built services. And this is something I think we need to pay a lot of attention to, because I think most of us went abroad to learn how to build product. We have to train our next generation to be able to build product in India. And I think this is a critical sense, because that's what's going to drive the design ecosystem and consumption of localized solutions. Okay? I always say that I'm always amazed at how many small companies in Germany make silicon products. You often don't realize them, but they're all localized solutions from, advanced regulators for plumbing to everything else, but they have their own ASICs in them. Okay? And they're not in an advanced node, but they do demand product engineering skills. Okay? Okay, so the question is, I would like to change from that to being a leading foundry. Okay? In the India context, this is a loaded question. Okay? What do you see at the needs of drivers for this ecosystem? What would your recommendation be, being a leading foundry to the government, what you think is missing, so that you could grow your business? Let's put it in a generic question, because the answers that you give are also relevant to anybody else starting a foundry. Okay?
Yeah, okay. I mean, at the essence of it, we are a business. Business, it needs to be profitable. We need to hit our ROE goals. And again, this is a cliche, but we follow customers. And where, we look at different geographies, we've studied all of that. Clearly our base has been Taiwan, but business needs will drive how fabs look at location, etc. Beyond that, I know when I got the minister's talk, etc., in the press conference, we're doing a lot of things on infrastructure. I also heard from other speakers, not only includes gases, etc., but even equipment. I mean, those are things. How quickly can you get replacements? Those are things that are important. Supply chain logistics. People, talent, you've talked about, Barun, and everybody else has. Very important, not only for the business end of supporting customers, whether they're internal to the same company with running that fab or external, and executing in the fab. And finally, again, this continuous stream of resources. And again, going back to the business end, any fab doesn't exist. It's not a standard chemical industry which just runs input and output. This is running a semiconductor fab is a complex operation. Products change on a yearly basis, 6-month basis, new standards. You've got to continuously tinker with the technology. So there's R&D money, there's product engineering money, there's resources you need to spend. So it's the talent. All these things together are the most critical things for any fab wanting to be successful. Now, I'll talk just a very little bit about what's made TSMC successful over the years, because it's somewhat relevant, right? And of course, you need financial strength and manufacturing. But we think there's three big pillars. And the first is, of course, the technology leadership. Now, technology leadership, again, as I said before, it's not only Moore's Law. It's all the differentiated technologies. And I think that's an opportunity for India. There is going to be a need, tremendous need for differentiated products using mainstream technologies. When I say mainstream, again, like you said, 16 FinFET and above, older technologies. So there's a wide range of technologies that can create products that are absolutely essential for the success of data centers, for AI, ML, all the wonderful things we talk about in high-performance computing. Couldn't be possible without companion chips. So that's number one. Number two, capacity. But you need capacity that you build in a place. It's got to be effective capacity. It needs high yield, good quality, good reliability, good, so people can sleep at night. The third thing is customer trust. And I think that's one of the most important things that's made TSMC successful. In fact, Tom Friedman did an article not too long ago in the New York Times about what's made TSMC successful is simply one thing, which is trust. And it's structural trust. We don't compete with our customers, but there's execution trust. You know you'll get your product when you want it. But I think the most important thing, these are three things TSMC controls. But Barun, I'll say this, and this is very close to you. The most fundamental thing that has also made us successful is the ecosystem. That's the IP companies, the EDA, the DCAs, the VCAs, cloud, 100+ partners, just like IMEC, etc. And what do? They enable ease of design, optimize your products, and more important, offer differentiation. So time to market, of course, and we call it the Grand Alliance. So Barun, now you can comment on that from your end, but that is absolutely the four things that are critical for any fab, or TSMC to be successful in this current time.
I think that's a very valuable comment, because I think for most people, if you look at it, it's not that TSMC has not had competition, but the thing is people have gravitated towards it. Okay, I think all of us have been designers at different types of this thing, and it's partly because they have essentially provided the most complete service, and in some sense made designers reduce the threshold of entry for many designers. Okay, it's to some extent why we go and shop at Amazon, right, or Flipkart, or anywhere. It's because it is the threshold, especially in the pandemic, the threshold of purchase was dramatically reduced, and this is something I think in particularly in India, we are very good at providing a fantastic service. Okay, I think it's something that in general we have appreciated for a very long time. We might not always recognize it as such, but I think we're quite demanding customers. Okay, and so that demands very good service. So I think there is some cultural identity with providing good service, and that's something hopefully will translate that the foundries in India will be better service providers than anybody else can. And one last item I would say, which I think is critical, is the whole design enablement and models, which is becoming more and more complicated as the diversity of technologies occur. Okay? And I think this is something where, because there are more resources available in India on the technical side, it could be a very clear added advantage and support ecosystem which can accelerate access to the technology. So I think this is something which it is something which I think should be emphasized in this part. So in the interest of time, what do you have any? Because I would like to finish on time. It's 11:30. So do you have any closing comments, Saji?
I'll say we've talked about all the drivers. We've talked about, just as a recap, what we need. I think we need to be aware that there's some pitfalls. I don't have to look too far. I mean, clearly, for example, in China, there's at least 6 fab ventures where they invested billions of dollars that folded. And I think there's some lessons to study. So it isn't going first, just building a fab for fab's sake is something that can be done, but doing it the right way will be a more positive way and self-sustaining way. Now, can we do it? I mean, again, just on a personal note, my father built clean rooms across India, both for pharmaceuticals and for defense, for many, many years before he retired. Can be done well, and so I have no doubts that we could have the ability to build fabs and run them without any problem. It's, again, let's look at the business proposition first before we go embark on a pretty expensive venture.
Okay, I mean, I think that's definitely, I think there's a lot we can learn from past mistakes. And one comment I would go on closing, this is the last comment I'll make before we close, is I think for the entire initiative in semiconductors, I think one thing which we can do a lot better in India than possibly any other ecosystem has done is the issue of inclusion and growing women engineers into the ecosystem from day one. That's one of the advantages you have when you're starting something new. And I would actually say that to enable this, and I was talking about this with Jaya yesterday, who I had not seen for a long time, I think the IIT should have a IIT which is women only and an NIIT which is women only. This would change the dynamics of engineering education for women and give it a boost. Okay? We should target on a much shorter scale the 35% or 40% women in engineering and technology that everybody in the West is now, that I sit down and target and worry about today. Okay? And this could be a completely new, of the same quality and scale, because if we are going to have a talent pool, having a diverse talent pool also matters in terms of consumption. Okay? And this is extremely important. If you're more than 50% of all buying decisions are made by women in this world. So that impacts product. Okay? So it's extremely important they're part of the engineering and design. And if we can change that, we would be a leader compared to anybody else in the world. Thanks, Steve.
Thank you.
Yeah, I think we'll just take 2 questions, yeah.
Okay.
Yeah, give Ali mic, Kodi. The mic will come to you, just hang on.
Hello? Yes, so I have a question. So as India is looking to establish multiple fabs, do you think the approach should be we standardize all these fabs to have a single node, and the government helps, and there is synergy between these different fabs. So is that the right approach that the think tank makes, that you take single, let's say everybody goes one node, 28 nanometers, and then all the fabs are developed on that? And if you think that's the correct approach, then what node should we target? 28 nanometer, 14 nanometer?
I would say this. This is going to, I think somebody said this is going to be a marathon. This is a journey, not an event. Oh, sorry. This is a journey. It's a marathon, okay? The semiconductor industry believes in marathons. That's how it has existed and won. So I think there's not going to be one size fits all. There is not going to be one solution fits all. If the government, like I said, that it would be an interesting, I think it will be a success if we are able to get one project started every year, which we believe has a potential for success. Okay? So if you say that you've got 4 applicants and one can get started this year and the second one, and hopefully some of the bigger multinationals come in as the market grows. So you will need all aspects of right from, Shiva argued about the if you just look at the gap in manufacturing capacity necessary to support all the applications, if it is a 100x gap, you will need the diversity in India of technologies to support it. Now, I think the issue here is, I do not think any of us will be smart picking winners and losers. Okay? I think the fact is you have to pick the best plan that you see at every time and support it. And I think over time, some will obviously go wrong. We would like to minimize that. Okay? But I think you need all the nodes. I think it's easier possibly in the earlier phase to focus on the mature nodes. But and the advanced nodes are still the forte of the multinationals. Okay? And so these incentive packages will have to be extended and encouraged over time. So this is a large journey, and I don't think you're going to see the first wafer out from one of these things in 4 to 5 years, okay? And that's the reality, okay? And in between, you got to do all the other building of ecosystem that goes with it, okay? Sajeev, do you have a different opinion?
No, I agree, and I think that's the important part. We're looking at a long horizon. It's not, I think Sailesh or Shiva talked about go where the puck is, and I think that's important. So technologies change over time. I mean, when we say 28 nanometers, we include in that everything that goes up to 22 nanometers. We are constantly tinkering with this to drive, better PPA and C, which is cost. So the business plan becomes the most important thing. What products are going to be created, what technologies are needed to differentiate those products and have the best performance 5 years from now. Because that's when something, the wafers may come out. Let's say you started today. So that thinking is more important up front than just building something that may not be the right thing to do.
Okay, any other question, or if not, we end?
Varun.
Hi, Satya. Okay.
Hi, Varun. Hi, Sajeev. Good to see you.
Hey.
So over the last 2 days, we have talked about various leaders, and you both talked about the business model and the business proposition should drive what we do, right? So if we look at the broader ecosystem, we have IDMs, we have memories, and then we have foundries both for silicon and compound, right? So do you think there is a kind of a roadmap or interplay between the three in terms of more from a business model point of view, not from a technology point of view, that what makes the most sense for India?
I think the question is that it will depend on what the proposals are.
No.
All of them makes. I mean, I think India is such a large and diverse country with needs and applications that I think we will be. If any of us say that this is like going back and saying that all of you should buy cars which are only white, okay, that would not make sense, right? So the question about it is that everybody should buy cars which only seat 3 people. Okay, so that's the type of discussion. So I think the question is, I think what is going to be the decision making has to come from the fact is, what sort of applications do you think people are able to load a fab up and get it going, and who has the most credible story for that? And as it doesn't matter what technology it is, and because we are starting from a very nascent ecosystem, okay? As long as you can build a supply chain around it, okay, from the suppliers and everything else, it will obviously have to be at some scale, because if not, you won't be able to build the ecosystem, okay? And I think every plan should be looked at for its credibility. There is always going to be some risk in it. I don't think we're going to ever say it's perfect. And you'll have to go. And I think today, since I don't have privy to all these plans, I can't say which is the best one to go, but I think you will find interesting ones. Okay. Sajeev, do you have a difference?
Yeah, hi Satya. So look, we have the building blocks, right? We have the ecosystem in place. I mean, we've dealt with so many successful IP companies. I mean, Cosmic, Sankalp, I mean, we can, and product companies, so we can, plus the designer, just the sheer numbers. I think going back, so I completely agree with Varun. We've got to look at the products and what they will need to drive success. And that's really, again, the key. It's, we shouldn't put the cart before the horse. Let's drive it the right way, but there's many opportunities as we look out in time. These, technologies will be constantly tinkered with. So you need to invest in technology development and manufacturing, improvements. And so it needs a self-sustaining model. The business has to make money. And that's what's important to think about up front.
Yeah, thank you very much. The keynote address is about this topic, India's resilience to semiconductor supply chain. So, though it's digital, I think it's our duty to welcome Sri Shiva Shivaram. Yeah. Video, please.
Good morning. Good to see all of you. Good to see all of you virtually. It's evening here in Silicon Valley. Yesterday, the Prime Minister was admonishing us to be practical in our advice, practical in our suggestions for what we need to do next. So I want to thank Minister Vishnu and Minister Rajiv Chandrasekhar for giving me the opportunity to talk to you all today. Next year would be my 40th year in the semiconductor industry. There are some in the audience, Ajit Manocha probably is sitting up front saying that he has been here long and he calls me a young man. But over these 40 years, we have seen vast transformations in the industry. In the 70s, the United States led the semiconductor industry. In the 80s, the Japanese got to dominate the industry. In the 90s, the Koreans started in. In the late 90s and the early aughts, the Taiwanese started their semiconductor expansion. In the last 5 to 7 years, the Chinese have been investing a lot of money into the semiconductor ecosystem. There has been a pattern in these developments back and forth. There are lessons to be learned. There are models to be emulated. There are pitfalls to be avoided. I want to spend some time talking about all of these to you with respect to our ability to have resilience. Let me see if I can share my screen. I'm assuming you can see my screen. So we'll talk about how do we ensure India's resilience. How do we make sure that in the midst of all of these semiconductor shortages and security issues, what do we need to do? I talk a lot, and my lawyers think that they have to tell you that don't believe anything this man says. So I had to put that up front. Let me talk a few minutes about Western Digital, the company that I lead. Many of you know us. The SanDisk brand is very well known. We outsell our nearest competitor 2-1 in India. 40% of the world's data sits in a Western digital device. There is a very large claim. 40% of your data, whether it is in your cell phone, whether it is in the cloud, whether you store it in your PC, 40% of the data sits in a Western digital device. Western Digital is the world's largest pure play storage company. We have the portfolio breadth, 14,000 patents and 65,000 employees, including a very large development site in India. The Indian development site has grown almost 10 times in the last 7 or 8 years. We are a big manufacturing company. We are the largest foreign investor in Japan, period. We are the second largest foreign employer in Thailand. We have been continuously having manufacturing operations in Malaysia for now close to 45 years. We have operations around the world, including, as I said, in India, and these 65,000 employees send you their greetings. We know how important India is to the global ecosystem across, not just in semiconductors around the world. We are fully present and involved in India's growth. So we've heard this before. India is starting up. 60,000 plus startups, more than almost 5,000 that have been funded. 83 active unicorns. I'm told there are more, but there are 83 active today. Because if you go public, you're no longer considered a unicorn, you are now a public company. So 83 active unicorns today. What they probably all are assuming that there will be the infrastructure that provides them to function. That infrastructure, of course, is provided by semiconductors. Let's look at this a little bit more carefully. What does semiconductor resilience mean for India? What are the objectives? What are we trying to do? First and foremost, we need to ensure India's national security. In the broadest sense, I don't just mean defense electronics. I mean the national power grid. I mean the national communication network. We need critical industries to thrive. Automotive industries, telecommunication industry, power industry, and my beloved entertainment industry. I need to be able to watch Dhoni and CSK win once more. I want to be able to watch my Bollywood movies. So entertainment industry. These industries, for them to thrive, you need to have semiconductors below them. And of course, data digitization are causing new creative transformative industries. Soon we'll have quantum computing. Soon we'll have DNA-based storage. We will have data-based new applications created. We need to lead all of them. And in the end, for the common man, we need to make sure there is manufacturing jobs that are high-paying, high infrastructure, high economic returns. So these come naturally. These are our overall objectives when we say we need to have resiliency in India. Where is all this data coming from? I took a look at it. In the last year and a half, just during the pandemic, there have been 17 applications with over 1 billion downloads and 37 applications total over time that have had more than 1 billion downloads. India has been downloading everywhere. Every one of these is producing data. Every video camera, every cell phone, every surveillance, all of these are producing data. And these data are producing a flood of growth. So here it shows how much these data is growing. The hard drives and the solid state drives are exploding in demand. Almost 37-35% year-over-year CAGR. To top it all, the amount of data that is actually stored is only 7% of the data that is actually produced. So we produce close to 118 zettabytes of data. For those of you who keep track of these things, a zettabyte is 10 to the 21 bytes. That's about the number of stars in the galaxy, 10 to the 21. That's the amount of data we are producing. And we are not storing a lot of it. And we need to figure out technologies to be able to store all of them and gain value. In order to gain that value, every bit that we produced, ultimately somewhere, someplace, a physical bit has to flip. Somewhere somebody has to store it. Then somebody has to go network it. Then somebody has to process it. That bit, in the end, becomes valuable only when we are able to process it, and that processing happens with semiconductors. Let's look at the semiconductor industry overall. Today, if I looked at the industry, it's about a $500 billion industry. Memory is the biggest component of it, followed by microprocessors and other application-specific integrated circuits like RF, wireless, power management, etc. And then an assorted number of minor categories like discretes, optoelectronics, non-optical sensors, analogs, chips. Put them all together, you get this $500 million of revenue. Memory is about more than or about a third of the revenue. And that's where we were talking about the amount that needs to be stored. The technology uses each of these, the fabs, in a slightly different way. A memory, every generation that comes in, replaces the existing technologies in the same fab and makes the same fab more advanced. Logic moves to a new fab, lets these old fabs get used by other applications. And these other applications use more depreciated fabs. Each one of them has a different way. Each of these big components uses the fab differently. And into these fabs go the capital equipment. And this marketplace is about just under $100 billion. The biggest, of course, we hear a lot about lithography. Lithography, where these machines could be $80 to $100 million each. Materials removal, deposition, process control, these kinds of $2-3 million pieces of equipment go into each fab, leading to about $10 billion of equipment going into each fab. And so the equipment industry is a critical part of that supply chain. In the semiconductor world, the closest to the original prophet is Gordon Moore. Gordon Moore one day went up to the mountains, prayed to the semiconductor gods, and came back and gave us our rules. And he gave us 2 rules. The first rule, the so-called Moore's law, talks about scalability. He said semiconductors are unique in the world. Every year on the same real estate, you can get more. Scalability is our ability to get more out of the same resources. We've been doing that now for 60 years. Scale, on the other hand, is our ability to use that scalability and propagate it up, make it much bigger. I'm going to talk to both of these, scale and scalability, with the context of those storage systems that we talked about. About 30% of all semiconductor revenues is memory or storage, and I'm going to talk about how the scalability and scale work, and you can now extrapolate it to other systems. So let's talk about one of the places where it has grown a great deal. This is DRAM. DRAM is used for storing those bits during processing. You can see as the data centers exploded around the world, DRAM production just exploded. It's continuing to grow. This looks very impressive till you look at how this looks in the presence of flash. That same DRAM in scale looks minuscule compared to how fast flash is growing. Flash is growing almost 3 to 4 times more than DRAM is going. And above that is hard drives. Hard drives and flash provide storage. They are 30 times more than DRAM and 2 times more between flash and hard drive. This is the scale. Those zettabytes that we were talking about has to be stored in one of these two things. Look at what this means. The flash NAND wafer production, you take the wafers annually produced by the NAND manufacturers around the world, you stack them one above the other. Just 1 year's production. Compare them to some well-known landmarks. That's the Eiffel Tower. You think, it must be about as tall as the Eiffel Tower. That is the Eiffel Tower in that scale. The Burj Khalifa is there. The annual NAND production is bigger than Mount Everest in height. The annual NAND production of wafers, if you just stack them, 12,000 meters, is a third bigger than Mount Everest. That's scale. That's how much these fabs are producing. I want you to give us an idea of how big the scale of these fabs is. We operate one of the world's largest fab complexes in Japan. This, next to Intel and SanDisk in Santa Clara, is the Levi Stadium where the San Francisco 49ers play football. Large stadium, almost 1 lakh people, 100,000 people can sit in it. Big stadium. Look at the size of it when you compare it to the size of the fabs that we have in one site in Yokkaichi, Japan. We need the equivalent of 9 stadiums that would fit in that one complex that produces 1/3 of the world's flash, that 12,000 meters of wafers get processed, 1/3 of it get processed through this. That, I want to make sure you understand, is scale. Those wafers then have to be then made into products. The USB sticks that you have in your hand, the SSDs that go into the data centers. The wafers come in, get assembled, tested, packaged, system integrated, and shipped out as product. In a typical day, almost 5 million die get processed within Western Digital. 5 million per day. In a week, 1.2 million SSDs get processed in that factory, which has got wafers in, SSDs out. So I want to make sure you got a sense of what scale is. This is what we need to reproduce in India over a long term. This is what we mean by scale. Now let's go to what scalability is. In that wafer is our ability to store the bits. I'm going to run a small video so you can get a scale of what's on that wafer. Let's see if this plays. It doesn't quite play like a video as I would have expected it to. So what it shows is 1 trillion of these holes that are as tall as skyscrapers on which these bits are stored. This is where the semiconductor equipment that is used to produce these layers, deposit, etch, and drill these holes are done. And you can see the progression of these skyscrapers over the last 10 years. In 2016, we made 48 layers skyscrapers, and now we are about to introduce 200 plus layer skyscrapers. This is the Moore's law on steroids. Whereas in logic, Moore's law is slowing down. In flash, Moore's law is actually ahead of time. Every 18 months, if you can see, 2016, 17, 18, 20, 22, every 18 months, a new node is coming in that can store 50, 60% more bits on each wafer. These are coming into high volume production, and those high volume production happens with wafers. Those wafers are on those mega fabs, and that mega fab produces that Mount Everest tall number of wafers. This is how scalability and scale work together. In India, if we can't get to a place where there is both scalability and scale, we would have failed. So the complexity of the semiconductor supply chain is the following. We talked a lot about what happens pre-silicon. Design, CAD software, IP blocks, simulation environment, emulation environment, verification. All of those things India is very good at today. We know how to get it done. Pre-silicon, we are good. Silicon processing, this is where fabs and capital equipment and materials. The fab, you can't think of it just, hey, I'm going to build a fab. The fab is more than a building. The fab is a business model. Given the capital intensity and cyclicality, requires a steady revenue growth so that this can pay for itself. It is a R&D receptor. It needs a constant flow of R&D to keep the scaling and scalability working. It is infrastructure intensive. Power, water, natural gases, waste recycling, people. We need to have the infrastructure that needs to be there. And of course, needs advanced personnel to run, maintain, sustain, and grow this. And once the silicon processing is done, post-silicon, packaging, assembly, test, system integration, application support. And remember, each of this is specific to those various categories I talked about. Whether it is memory, whether it is flash, whether it is DRAM, whether it is logic, whether it is ASIC, whether it is power, whether it is high voltage, high power, low power. These are different for these, analog. And this semiconductor supply chain is what we need to recreate. So let me conclude with how do we focus on this in a big picture. Today, no one country has all the pieces for a semiconductor self-reliance. It's impossible. Materials come from one place, equipment comes from another place, technology comes from another place, design comes from another place, finished product goes to a different market. Every place is different. So, the first and foremost lesson is security comes from well-developed alliances. We need to make sure that we are well allied with friendly countries and friendly companies and friendly nations and friendly corporations and multinationals so that we have security, because we can't do all of it ourselves. We shouldn't try to do all of it ourselves. But we need to be aware of the needs. What specific industry is so important to us that I need to make sure that we have that ready. We need to play to our strength. Our strength is our people. We need to play to our strength. And we really want to make sure we establish roots of trust in the supply chain. Defense electronics in particular, having secure fabs to make sure we know where we are getting our semiconductors from, that I can trust that supply chain. That is very important. Wayne Gretzky, an immortal hockey player, used to say this. Why are you so good at hockey? Somebody asked Wayne Gretzky. He says, you know, I skate to where the puck is going to be, not where the puck was. For us in India, it is important that we realize we need to know where the puck is headed. And we want to make sure we focus there as opposed to doing something historical. Where we were before the pandemic is not where we are going to be. We need to make sure we are looking forward and not backward. And this point gets lost often. Japan used to be a leader in semiconductor till they focused entirely only on the production of semiconductors and lost sight of the applications and the markets. They did not develop their own markets. And soon enough, the companies that were leading at that time, the NECs, the Hitachi, the Toshiba, the Mitsubishi, the Panasonic, lost their leadership in semiconductors. Leadership in applications and markets need to be there if you want to have the continuity of the industry. So if you think about it in a big picture, we don't want to do everything ourselves. We want to make sure that our well-developed alliances, we need to know what is important to us so that we can play to that strength. We want to make sure there is always a supply chain root of trust. think forward, not backwards, and I want to make sure we focus on the leadership in applications. So I have given you a few ideas of what it means to have security in semiconductors. Our semiconductor religion is based on scale and scalability. We need to make sure we are enforcing, we are looking ahead, we are making sure we are developing those alliances so that we can leverage the immense strength of our people to lead for the long term in the semiconductor industry. Thank you so much.
A couple of questions can be asked to him. Yes, and you can raise your hand, the mic will come to you. Mr. Shiva, can you hear us?
I can hear you very well, thank you.
Yeah, okay. Anyone? Yes, there.
Mr. Shiva, this is Raju Koduri from Intel. Nice talk, really enjoyed it. You started off with saying Prime Minister Modi wanted some practical advice, practical solutions. Unfortunately, I missed his talk, and I'm talking right after you, and I was a little worried how practical my asks would be for here. But I have to ask you, right, that after, now I want to ask, can we build your memory stack of the size of Mount Everest and solve all of India's storage needs? Is that something we should, is that practical?
So I have been talking with Minister Vishnu, Minister Rajiv Chandrasekhar about these things. I am willing to dream. I am willing to come here and say that a fab complex in India is indeed possible. People say pioneers get shot with arrows, but somebody has to be a pioneer. There's a often repeated joke in the Silicon Valley that says that I don't know what comes first, peace in the Middle East or a fab in India. I'm now willing to say that we probably will beat it. We will have a fab in India, and we will have sooner than later a fab that we would be proud of having in India. Did that answer your question, Raj?
Yes.
Thank you, Mr. Shivaram, for... There's one final question. Yeah, go ahead, sir.
Dr. Shiva, I was looking at your map of manufacturing sites. There is one red dot missing there.
You now know why I'm here. I'm talking to you. I'm talking in front of all of the ministers. We have a very large development site in India. Our engineers there have been asking me the same question. India has been, our employees, our contributors, our partners in India, we are getting folks from all the major institutions, the IITs and the NITs here. And we measure their productivity today by how quickly they produce a patent. And India has been now setting records, new college graduates from the time they come into the company to how quickly they produce a patent. We've been very, very productive there. Now it is time for us to seriously think about how we can go from a development site to now actually making the products that they are designing and developing and marketing. So we are looking at it, and I'm glad you noticed the absence of that red spot in the heart of India.
You can do also. Michael, yesterday people mic'd up, right? No, you can do that.
Shiva, this is, good morning, Rajiv Chandrasekhar. Thank you for that excellent presentation. On some days I require a boost and some confidence as well when on this mission that we've set out on, and this presentation was extremely, confidence boosting even for us. Quick question, what are the issues that you see for somebody like Western Digital when you look at India and consider or evaluate making an investment in a fab? What are the top 2 or 3 issues that you think we should be focused on?
So, Minister Chandrasekhar, thank you for having me here and allowing me to talk. People talk in terms of infrastructure first. Or can you have water? Can you have the land? Can you have natural gas? Can you take care of the waste? Can you produce the power? They are needed, no question. The infrastructure with respect to how do I have a capital equipment maker come and have his spare parts ready? Can I move it in and out of customs very quickly? Can I deliver it? Yes, these are solvable problems. What I do need, however, is this: a motivated, talented work base that I can count on from all levels, from operators to technicians to sustaining engineers to development engineers to PhDs and material scientists and physicists that need to come through. When I have that infrastructure reproducibly here, they will solve all my problems. In the end, all problems are people problems. People will always solve the problems. That's my confidence here, Mr. Chandrasekhar.
Thank you. Thanks, Shiva.
The compound semiconductor, India's way forward. I would request the moderator, Mr. Vivek Sharma, to kindly come over. Ladies and gentlemen, let's welcome Mr. Vivek Sharma. We also have the other speakers on the virtual mode. We have Dinesh Ramanathan from NextGen Power Systems. We also have on the virtual mode again Primit Parekh from Transform, Harshad Mehta from Silicon Power, and on the physical mode we have Anant Naik from Gaitek, Mr. Anant, and Seema Vinayak from SSPL DRDO, and once again Amitava Das from Tago Technology will be on the virtual mode. Mr. Vivek is the Managing Director of ST Microelectronics India and is responsible for the company's overall strategic operations. He started as an engineer with SGS Thomson and post-working for ST in France. He took up senior positions in R&D, admin, sales and marketing, and strategic leadership roles. So he'll be moderating this session. So Mr. Vivek Sharma, it's all yours. Yeah, over to you. I think it's on.
Is on?
Yeah.
Yes, okay. Thank you very much. So I think this is really a great pleasure and honor to be discussing on something where Professor has already put up a very strong foundation. I think we are already quite convinced about this new technology. But in this panel, very interesting panel we are having. We are starting from the materials, going way all the back, I should say, for the market and the applications, and also understanding the challenges which would be happening. Before we do that, maybe I will just take a few minutes to set up the business case and emphasize, which Professor, by the way, already did. If we see that today, world over, whatever energy or whatever we do, by the way, one thing what is needed is energy and power behind it. Without that, it cannot work. 23,000 terawatt hour is seemingly the energy consumption which was there in 2019 and 20. And there is forecast that it will grow 30%. So we are looking about 30,000 terawatt hour which would be consumed by 2030, which is a lots of energy as we can see. And rough breakup of this is about 40% is consumed by industry and then remaining commercial and residential. So if we look at 40% and taking 25,000 terawatt hour, this is about 10,000 terawatt hour. Even if we gain 1% energy efficiency, just 1%, which would be about 100 terawatt hour, this is estimated to be equivalent to 15 nuclear plants, or is about 30 million equivalent carbon dioxide, pollution which is done there. So it's lots of, I should say that, gains which we can do if we can just focus on the energy efficiency. Now, one thing which when I was looking at it, there some wisdom of Upanishads was coming to mind, which was saying that man eva manushyanam karanam bandhan moksha. That mind is the only instrument by which we get attached to the world and is the same instrument by which we can get detached to the world. Similarly, if technology has brought us where we are in terms of consumption and this carbon issues, only technology can take us out. And that's where this new materials are playing a big role there. And let's now try to understand and see that in terms of dollars, what does it mean? So if we look at silicon carbide today, estimation is that it was about $1 billion in 2021, and as already indicated, but that was for gallium nitride. But looking to silicon carbide, it will grow to about $5 billion by 2026. So from $1 billion to $5 billion. Similarly, and there the majority consumption is going to be electric vehicles. And if we know that, about 9-10% is the penetration of electric vehicles, and it will reach to about 20% by 2025, because electric vehicle is a great system to save in terms of all the pollution what we face there. In terms of, just to have an idea, that in terms of weight, also internal combustion engine is about 100 to 250 kilograms, whereas an electric motor would be just 75. And then the pollution level would be much lower. So silicon carbide, a lot is being driven by the electric vehicles. And this will continue, as we know. Then gallium nitride, we already heard, but I will just put the numbers. I think some numbers were already indicated by the professor. If we see on one section, which is the RF section, and we have defense and telecom infrastructure, quite a lot user of that, is about in the range of 700 million to 1 billion. It will grow 2.5 times in next 5 years. So would be reaching about $2.5 billion if we look at the RF side of gallium nitride. On the power side, where the consumer is a big, like fast chargers, for example, which was already indicated, and this is at the moment is about 100 million, but this is also going to become about $1 billion as we will reach for next 5 years. So if we are putting everything together, there are two elements here. One is that we absolutely need this technology, because otherwise the more and more power we are going to consume, if we do not gain in the efficiency of that, it would be pretty bad for our planet. And great news is that this is available today, and we should utilize it more and more, and the business case is very clear. So in that context, I would like that we open our panel and going from one side, even starting from the research, materials, way to the application and all the challenges there. So once again, very pleased to have this very diverse panel in front of us. So maybe I start with from you, to begin with on the right side from SSPL.
So thank you, Vivek. It was great listening to Professor Umesh Mishra just now, because it felt so much, I felt so much at home with compound semiconductors. We've been listening to silicon industry and how it is growing over the years and how complicated, almost equivalent of about 120 stories of a building. I would say that SSPL, Solid State Physics Laboratory, it was born out of a remarkable vision about 60 years back to build up semiconductor capability and a knowledge base in the country. And what we feel is that long back, somewhere in 70s, we thought that silicon is already a mature technology, and so it is the compound semiconductors that we should move forward with. And as we went on, about, after developing a few circuits, devices for RF applications in gallium arsenide, What we felt was that unless you have a foundry, a fab, where you can take your technology, you can actually not have your technology can actually just die down. You built it, but where do you take it? We did not have anything like that in India. And so about 30 years back, I think around 95, we went ahead to develop GETEC. And GETEC has been delivering gallium arsenide MMICs for defense and space applications. So once the technology we could see in production, we went on to gallium nitride and silicon carbide, and out of experience I would say that since our mentors always thought that if you are developing a technology, it is very, very important to develop the material as well. So right from ingots to epitaxy to device design and device fabrication, and then going on to measurement, and then say the process design kit based on the GETEC foundry. We've seen it with gallium arsenide, and we are doing the same with GaN now. But what is very important is that silicon is really very, very mature and very, very complicated, whereas compound semiconductors, because as you would have heard Dr. Umesh Mishra mention, it is just by changing the growth of the material, you can actually, without going down to even if you go up to about 250 nanometer, you can reach frequencies in the Ku band, and you can deliver such high powers with such high efficiencies. So the promise is very high. And what we have is that in the power sector, again, silicon carbide, gallium nitride is holding a major promise. Also, people have started working in the digital arena, seeing how gallium nitride can be utilized there. We also have lighting, of course, is something where gallium nitride all started. So there is a very, very vast area. Now quantum is coming up. Gallium nitride is showing promises to be utilized even in the quantum technologies. What I feel is that yes, this area definitely needs thrust. And if we have a foundry, a fab in compound semiconductor, the positives are that most of the universities, the IITs, the IIC are working in this area. So we have a very good human resource available with this kind of expertise that we can leverage. And the challenges are that the infrastructure that is needed for this, we have limited expertise within India. Of course, I heard Mr. Dalal saying that his father was involved in the building up of many clean rooms within India, but I would feel that there is a limited expertise to give that kind of infrastructure or the facility that is required for a fab, may it be silicon or may it be compound semiconductor. For compound semiconductor, I would say that yes, we may not require to be dependent totally on foreign, import of technology. Silicon, there is absolutely no other option. You have to get it from outside. But once we have the fab, how do we maintain it? Because if we want to get maximum out of minimum effort from the workforce, it is very important that all your equipment and your facility is continuously running. And therefore, we need experts in this area as well. Then the semiconductor equipment, we are totally dependent on foreign resources. There, the export licenses, the numerous delivery period extensions, and sometimes the after-sales support all become challenge. And therefore, it is very, very important that we have some policy decisions where either we go ahead with very long warranty periods, or we have the OEMs establish their spare part service centers here in India. I would just say that this is the time that requires a lot of planning. And I also hear that this is maybe the third of the efforts, which is really wonderful coming here. it is so overwhelming to see the numbers that are involved in the semiconductor industry within India. But this is the time to actually plan and see what were the reasons, what were the causes that the first two attempts or maybe a first few attempts did not actually have, let India have a fab. And we must have one here now. So it is learning from that, and whatever way we can make the establishment of this technology easy for the people who are bringing it here, it is very, very important. We have to depend on very intelligent collaborations, which is a must for bringing any fab to India, and also a major support in terms of equipment, in terms of chemicals, gases. I think that since yesterday that has been discussed. And there I would say that because there is limited demand that exists within the country, we do not actually have people who are working in this area, but once we have a good semiconductor setup within the country, there is no dearth of expertise even in this area. So with that, I would just say that we go ahead with Vivek.
Thank you very much, Seema. And I think that being there and really doing the kind of technology development and some of the challenges you highlighted are quite important, particularly if we would like to really develop it in a stronger way. So let's now move towards the left side of mine, where we have Anant and the GATEC model, as Seema was already mentioned. And would be really nice to hear from him the challenges, and particularly on the overall ecosystem. How do you see in India, how is playing it out?
Yeah. Good afternoon. First of all, I think the government has taken a very necessary step in establishing the foundry system in India, fabs in India, and I think METI is doing a great job of trying to bring together the stakeholders here in today's meeting as well as in the previous as many meetings that we have had with METI. So all the best to all of us. We will be able to do a great job to our nation. Now coming to the compound semiconductor, the way forward is the theme of today's panel discussion. And compound semiconductor actually is like in silicon, there are technology nodes. In compound semiconductor, besides the same technology nodes in terms of minimum feature size, there is a material node also. Like in compound semiconductor, there is indium phosphide based devices and MMICs. There are gallium arsenide based devices and MMICs. There is gallium nitride based MMICs. And also to a great extent now silicon germanium BiCMOS is also entering the field for certain front end radar applications, seeker applications. So I think the totally different paradigm compared to a silicon fab. This is more of a strategic and necessity for any country to have its own basic minimum requirement in this area. Like other than the defense applications in radars or electronic warfare, there are a lot of commercial applications. A lot were highlighted by Professor Mishra, who the team is already a leading team for gallium nitride and silicon carbide activity. Then there is a power conversion, which we have been talking about, the minimizing the losses using gallium nitride based power switches technology. Then we are also entering into a paradigm of terahertz technology, where compound semiconductor will play a very big role, and subsequently the quantum computing that we are entering, and in the world over is a huge amount of work being done in quantum computing, and the low temperature operations of these devices, cryo applications of these devices. So a lot of things are required to be done to be in tune with the time that world is progressing, and there are certain things which India needs to take at this time. we may require more than 2 or 3 additional kind of a compound semiconductor fabs which may focus on various aspects. Particularly the strategic aspect has to be kept separate, because these are the devices and MMICs which are not supplied to the country, any country. It is a IP of that particular country who will not share that easily with any other, unless we have a government-to-government understanding. So that is one aspect that we should focus on, that wherever there is a need and we don't have a way out, there should be a government-to-government understanding. And we also need to focus on all this compound semiconductor and start beginning to build certain fabs which are catering to different applications. A lot of manpower and institutes are working in this area, including IITs, regional engineering colleges, and IISc, for example, is taking a very big lead with the GEC approach. So I think people are there and we need to work together to come at a good solution for our country. And the biggest challenge to establish country is the supply material, which has been discussed n number of times since yesterday. For compound semiconductor, even the wafers or the substrate material is also a big challenge, besides having challenges in terms of photochemicals or other high priority material used for electronic fabrication. So we also need to have a foundry which can cater to this substrate material. Though we have some indigenous effort in development, but to start with, we need to have a head start. We should have a proper substrate like silicon carbide or gallium arsenide or indium phosphide type of a substrate manufacturer. The technology, know-how about the growth, etc. is always available in India, because many groups are working in this area. And coming to the chemicals part, I think since yesterday we have been discussing it, and India is a very big chemical industrial base. If you go to the western part of India, the GIDC we call, and maybe we are one of the biggest manufacturer of IPA, which is one of the big chemical, large volume chemical required for semiconductor industry. So it's only a matter of time that we can promote them to purify their material for electronics. There's 6.9 or 7.9 grade purification. So I think was talking to some, I think yesterday to MIT team, then they said yes, they are also including this subsidiaries also under this same platform, and they will be given some PLI kind of an incentive also. So that's a good initiative, and I think compound semiconductor fab is absolutely necessary for our strategic applications. And long time when DRDO set up this foundry with the technology that we have developed at SSPL, and we brought that technology to production level. Now it's used for space applications also, and I think we have a very good collaboration and support from ISRO in building this fab and using this fab to best benefit of the country. We need much more number of fabs in this field, I think, and this scheme should bring more fabs to India. Thank you.
Thank you, Anand. So I think very clearly emphasis is definitively as a country we need it. The world needs it more and more, as highlighted already. But also there are challenges, and this support from government is indeed very much desirable and applauded. But then the supply chain and ensuring that all across, because it was amply mentioned before that at the end we are quite an integrated ecosystem, just not isolated. So we need to focus on that so that everything can flow. So this is what we heard from both colleagues working here in India, from Seema and Anand. Let's now go over and go to Harshad from Silicon Power to share his experience. He has a very good experience in India, but also now operating from states. So let's hear from him what are the different challenges and opportunities he sees. Over to you, Harshad.
Thank you very much. I appreciate the opportunity to talk about and be part of this esteemed group. I talked to our new Secretary of Electronics about for an hour on a Zoom call, and something that he said was music to my ears. And he said, power electronics is the lowest hanging fruit for India, not only for silicon carbide, gallium nitride, but also for silica. And this is what we have been doing. So I know a lot of people don't know, and I understand that, but that is why I'm trying to make sure that we know. In Baroda, we have been fabricating silicon power silicon thyristors, diode, and so forth since 1998. And we not only supply to Indian industry, Indian railways, Indian process industries, we also supply to US military. And now we are going forward in terms of trying to learn and leverage the experiences and the lessons that we learn from silicon on the application side, because of the fact that if you look at the customer base, at least in power, you're going to have same customer base in terms of industrial customers who are using silicon as well as silicon carbide or gallium nitride at some point. And to be very honest, I think I'm very pragmatic, because sometimes customers are looking for cost-benefit trade-off. And very likely, they may go with a hybrid module first, with a silicon carbide diode and a silicon thyristor, because of the fact that silicon carbide diode provides 95% of the benefit of all silicon carbide module at only about 20% premium in price. So when you look at the cost benefit, sometimes you can't ignore the lessons we learn, and the silicon expertise can help us how we can commercialize silicon carbide as well as gallium nitride. At Ratan Shah, which is my company in Baroda, we already have installed a silicon carbide epi reactor, and it should be able to produce silicon carbide epi layers for not only for India but also for global industries. And that would start sometime in July of this year. So we have a three-phase plan. Phase 1 is a silicon carbide epi. Phase 2 is silicon carbide fab, and phase 3 is silicon carbide packaging, because as Professor Mishra said, thermal management is very, very important as well. And silicon power has for years, we have a very substantial intellectual property in terms of how to take advantage of high temperature, lowest inductance on the power device packaging. And so we are moving forward in phase 1. We already have started phase 3 effort, and I have a fab in US, which I purchased from Microchip, that does silicon carbide fabrication. So that's the plan in the beginning, near term, and then as we move forward, we will have the silicon carbide fab as well in Baroda. And that's the plan. Ratan Shah also has applied and preparing a proposal for gallium nitride, specifically for power applications and so forth. I totally agree in terms of energy efficiency. I totally agree in terms of having a fab in India so that the talent coming out of our institutes can be fully utilized. Our very first technical person on the EPI was from TIFR PhD, and he had an issue. He said, where do I go? He didn't want to go to Singapore or outside India. And he found a place to come to Baroda and work for us. So we are doing everything we can as a small company. Ratan Shah has been in the business in power semiconductors since 1969. It's been a public company since 1984. He's been an IR licensee from 1984, and then when I purchased Silicon Power from General Electric, I also transferred high power silicon thyristor technology to Ratan Shah as well. So I think we are trying to, my motto is commercialization. My passion is commercialization, and I believe in manufacturable, usable, sellable technology. And a second thing I have, which is not very smart business thing to do, but I also believe in why not. So in 2000, when there were no fabs in India, we transferred GE Silicon Fab, lock, stock, and barrel. It took us a year, but we are successful, and we plan to do same thing for silicon carbide as well as gallium nitride. Thank you very much. Appreciate it. And any question, I would take it anytime.
Thank you so much, Harshad. So we can clearly notice that the deep experience you have, and now as the time is becoming even more ripe for the acceleration of this would be definitively very handy for also our other colleagues who are in this venture. So thank you, Harshad, and then we will return back to you in case of questions. Now let's go to the other side, that when we need to develop a new technology, how challenging it could be. Professor Mishra actually indicated that, but it is my pleasure to invite Parmeet again from States to be able to share with us the experience of Transform. Parmeet, for you.
Thank you, Vivek, and pleasure to be here talking about how do you realize value with new technology, and in this particular case, gallium nitride, which is the highest efficiency semiconductor for power conversion. So, first of all, as many of you are aware, semiconductor development is a marathon, not a sprint. What are some of the requirements? Vivek and Seema and talked about it. Anant, human capital, financial capital, intellectual property, infrastructure, and infrastructure for semiconductor. Ecosystem, not just a semiconductor, but from chemicals to the semiconductor, to the user, to the application. Markets, and then policies. So I color-coded this stoplight chart, red, yellow, and green. Red means not quite present in India, and green, it is available, and yellow is improving, right? So human capital for semiconductors human capital is plenty, extremely well good in India, but not so much for semiconductor if you look at it from an overall perspective. Similarly, infrastructure and policies. What is entailed in a new semiconductor like gallium nitride, right? And it is a minimum 10 plus year cycle to get there. First of all, device development and operation validation, followed by manufacturability, realization, and product qualification. That's just kind of the beginning, you do all of that. Then reliability methodology and lifetime establishment, application development and marketing, QA, quality assurance for very low defect density. Power is a very unforgiving market, and PPM level failure rate. We have a Transform less than 0.2 fit rate, failure in time per billion hours of operation, with more than 40 billion of hours of operation with our customer system in the field, which leads to happy customers, is a sign of good technology. Field failure, very low field failure rates from mass production ramps, and at the end of the day, satisfying multiple growing markets with performance and cost benefits. And on the right side is shown some extremely large markets for power semiconductors, in which gallium nitride is not only inserted now, but rapidly growing. Smartphones and computers, 5G. 5G for RF, Umesh talked about it very nicely. Electrification, electric vehicles, four-wheelers, two-wheelers, three-wheelers. This is a huge opportunity. And we have a chance to creating business and societal value through technology. And how do you do that? How do you maximize learnings? And especially in a country like India, where this is kind of starting, not so much from scratch, as Harshad said, but in the case of a new technology like gallium nitride, kind of from scratch. Maximize learning, not by starting at the beginning, start at the finish line. And what do I mean by that? What is a typical manufacturing flow? You have the core, very fundamental, this is critical, epi-wafer technology and manufacturing, wafer fab, device design, wafer fabrication, OSAT, assembly and test, packaging, design and EMS, application design, EMS, and then system insertion. To do that, if you start from here, it will be a very long time. So start backwards. How do you maximize success? Start with what is existing. Use gallium nitride based power supplies, converters, inverters for products and systems. Build user confidence today. Then what do you do after that? Establish design centers, or in parallel with that, for application system development with existing state-of-the-art gallium nitride power devices. So grow the market. Cater to domestic needs. Then develop OSAT, assembly and test, with known good gallium nitride wafers, with something that works. Ensure packaging success. That takes 1 to 3 years, perhaps. Then come to the complex part, which is establishing wafer fab manufacturing. And not necessarily everything has to be in serial, but this is kind of the flow to maximize success at every step. Establish wafer fab manufacturing, including the associated infrastructure with proven started epi materials. And then complete the supply chain with epi wafer fab and manufacturing. Right, this way, what you will do is ensure success at every step by using established learning and established successes. And what is the goal at the end of the day? Vivek talked about efficiency. It's exactly similar what I show here. 150 terawatt hours, which is enough for all rural households, can be saved just by using gallium nitride widespread in power electronic applications by 2030. So this is efficiency across the spectrum to create a very lasting impact. And what we are doing at Transform and many other companies in gallium nitride, where we are leading the way, is having products, having gallium nitride in power conversion across the spectrum of the power range. From very fast adapters and chargers ramping in the market already today, sub 100 watts for your phones, tablets, iPods, etc. Motion control, industrial power, gaming power, two-wheelers, three-wheelers, as you go to the higher power range, data center and communication, the backbone of computing, electric vehicles, renewable energy, UPS, and for the EVs at the end of the day, onboard chargers, converters, and the powertrain inverter. Gallium nitride is a fascinating material. Power electronics is a very large growth market, and not only creating technology, creating business, but creating a long-lasting environmental and societal impact. Thank you, and we'll be happy to take any questions at the end.
Thank you, Prameet. And once again, I think that the business case is very clear, and also one important aspect is that the ecosystem is important. It's not only a matter of fab, but then we need also a rich ecosystem around it. Now let's move to Amitav from Tagore Technologies, and hear from him that his experience, particularly from the demand side, because we do have supply side where we have material R&D, development of new technology and fab, but what about the demand side, particularly in India? Amitav, up to you.
Yeah, can you hear me?
Yes, very well. Please go ahead.
Oh, okay. So basically, I want to focus on the demand side, and in fact, as an example, we'll start with Tagore Technology. So basically, what we did about 4 years ago, we created a team in Kolkata, and we started developing GaN IC. And essentially in 4 years, the team started from the defining the IC, they designed it, we sent the design to Taiwan, of course, because we don't have a fab in India, and we got it assembled, and the parts came back to Kolkata. And then it got tested, characterized, and we did the reliability evaluation. And the whole thing actually is done right here in India, in Kolkata. And then we developed the application, and now we are shipping in very large volumes to China. So not importing, actually exporting to China. So this example actually says that we can do compound semiconductor development right here in Kolkata, in Bangalore, in Hyderabad, and essentially what we need now is wafers. So basically, I think this whole proposal from government is exactly very well timed. So essentially, from the demand side, companies like Tagore and other companies will come, and I think there is a real demand, and we ourselves can easily, let's say, if it takes 2 years to create a GaN fab, we can take several thousand wafers in 2 years and provide the demand. So basically my point is that the GaN fab, if we can make the fab, because we are fabless, so we don't go into the process and how to make it, but assuming that we have that expertise, there will be sufficient demand for wafers, and I think companies like Tagore and other companies coming through DLI schemes will be able to provide the demand pool. Now I also want to touch on a few other related topics. So for example, once you have this fab and you make the ICs, where do you sell? Of course, we can follow the same thing right now, selling to China and other countries. But for that, we need competitive pricing. So I think we need some sort of incentive from government on wafer pricing, because the input material cost, chemicals and other things will make the wafer cost in India slightly higher. So that needs to be kind of compensated. So that's one aspect. But besides selling GaN ICs globally, I think another big opportunity in front of us is how do we develop a local demand within India? How do we develop demand in India? And you know, basically the EV space and solar space, there's really great opportunity in compound semiconductor. Why? Because the systems are complex, but not as complex as developing mobile phones, right? So a small, good team can develop systems and indigenize the product. But the biggest threat actually is the low-cost import. So nobody wants to develop their own system because they can import a complete knockdown kit easily. And what I found by talking to various people in India is that the quality of these cheap imports are not always good. In fact, the reliability is a big issue. So one proposal I have is that if we can have some more regulatory, like quality regulation and some sort of, and the customers, if they demand good quality, then I think we should be able to fight the cheap imports and develop an indigenous ecosystem for consuming the IC. So we can sell globally, or better even if we use the EV and solar space to develop indigenous solution. And we have to make sure that we weed out the cheap imports through some quality metrics. And the third item that I want to highlight is there is this big EMS, electronic manufacturing opportunity in India, right? And if we can define some schemes where they will be incentivized to use ICs which are fabbed in India, that will also give a good avenue for consuming the IC. So in summary, how do we create a demand pool of ICs made in India? So one is we sell globally. Two, we try to develop indigenous solutions and making sure that the cheap imports are weeded out through quality requirements. And number three, try to insert the ICs which are made in India in the EMS system through some sort of incentive scheme. So that's roughly what my thinking is, the way forward to create a demand pool to support a fab, because fab has to be full, otherwise the cost will not be favorable. And I think companies like Tagore and similar companies will come up with the DLI scheme, should be able to support the fabs. Thank you.
Thank you, Amitav. I think once again we have a very clear emphasis that we need the ecosystem, not just parts of it. And here Amitav brought one important aspect, because many times when we look at the demand, we see the demand as consumed by the consumers. But for the industry in semiconductors, there have to be system designers and system manufacturers in between to bring the real demand over there. So thank you. I think Amitav then later on we'll get back once we are through our panel. So now let me move to Dinesh from Next Gen and particularly how important it is for the industry and government to work together. Dinesh, over to you.
Thank you. So let me just quickly share my screen. I put a short presentation together that I can cover here. So first of all, thank you for inviting me to be on this panel. I really appreciate it. This is something that I fundamentally believe in, compound semiconductor. Number two, the fact that the government is taking a major initiative in developing the fab ecosystem inside of India. So I'm going to talk to you a little bit about next-gen power systems, and I'm going to give you a real-life example of how government and industry collaboration actually yields technology that is completely differentiated in the marketplace, and I'm going to show you some examples of it as well. Now, unfortunately, this is a collaboration that is with the US government, the state of New York, and next-gen power systems. but a similar example can obviously be working with the Indian government as well. So let me jump in here. So one of the key pieces of technology that NextGen has inside its arsenal is a vertical gallium nitride transistor. So you heard a whole bunch of people talk to you about gallium nitride devices so far. Most of the devices that you have heard about are what's called gallium nitride built on a silicon wafer. We are probably the only company on the planet that is actually making gallium nitride on gallium nitride devices. So what's the difference? We actually buy a gallium nitride wafer, and you can see that as the slightly darker blue indication in this cartoon of our device. And on that gallium nitride wafer, we actually grow this drift layer, and then we pattern the device appropriately. Then we grow P-type gallium nitride, and then we make a vertical device. The reason this device is vertical is because current flows from the drain, which is the bottom of the wafer, to the top of the wafer, which turns out to be the source. And this is an E-mode device, which means that the gate, when the voltage on the gate is 0, the device is off. When the voltage goes past threshold, which in this case is 1.4 volts, then the device turns on and the current flows from the drain all the way to the source. This is an EJ-FET. E stands for enhancement mode, which means when the device is turned on, it is off. You have to put some voltage on it to actually turn it on. We have over 100 patents on this type of design, the drift layer growth, manufacturing process, and this entire device is actually manufactured in a fab that NextGen has in upstate New York. This is the picture of the fab that we have in upstate New York. It's a 66,000 square foot facility. It's on a 14-acre lot. It's 20,000 square foot of clean room. There's over $30 million worth of tools and machines that we have installed inside that fab. And it's the world's largest GaN dedicated fab, both for R&D and for manufacturing. Now, the way this fab came about is a collaboration between the state of New York and NextGen Power Systems. So the way our deal with the state of New York works is this facility is owned by the state. NextGen Power Systems has a 10-year lease on this facility, and we have the exclusive ability to renew that lease for another 10 more years. The advantage of having this facility is that the amount of money that got spent into building out this facility is roughly $110 odd million. And if a company like ours had to raise $110 million to actually build out this facility, it would have been almost impossible to do. So this is a classic example of the state and a company like ours collaborating together to make this facility into a gallium nitride oriented facility and using such a facility to produce state-of-the-art technology. Now, what do we make in this fab and why is it so different? So I put one slide here that compares our device, which is a power device, and all the other technologies that are available in the marketplace today. So what I'm looking at is silicon carbide IGBTs, super junction MOSFETs, that's the third column, silicon carbide MOSFETs, GaN on silicon HEMTs. Professor Mishra covered this. You heard about silicon carbide MOSFETs. And then this is vertical GaN EJ-FET, which is what we make in our fab. So I'm not going to go through each of these line items, but essentially all the check marks tell you that all the features that are exceedingly important for power engineers to build power systems are fulfilled by what we make in vertical gallium nitride. Essentially, the device that we make is actually a union of the features that silicon carbide MOSFET offers and the features that a silicon GaN on silicon HEMT offers as well. So we'd like to think that vertical gallium nitride utilizes the full benefit of a gallium nitride material and makes a device that's actually purely gallium nitride. It has no silicon, it has no aluminum gallium nitride, none of these more interesting material structures in them. It has N-type gallium nitride, P-type gallium nitride, and metals that actually allow you to make ohmic contact to them. So from here, and this is the uniqueness of NextGen as a company, we're a vertically integrated systems company. So not only do we manufacture the semiconductor that I showed you in upstate New York, we actually make full-blown systems. So from the fab that we make the devices, we actually then make controllers, which we need in order to fully utilize the capabilities of the device that we're manufacturing. These devices are capable of running at 10 plus megahertz switching frequency, and there is no controller in the marketplace that will allow you to run those devices at these switching frequencies. So we make those controllers ourselves. In addition to that, there's a significant amount of work that has to be done on the hardware front, especially when it comes to thermals, magnetics, and other layout parameters that you have to be careful about when you're trying to operate power at very high switching frequencies. So we put that entire infrastructure together and we have created a scalable power platform. That scalable power platform not only allows us to make 20, 30 watt power supplies, it actually allows us to go from 20 all the way to 10 plus kilowatt power supplies, which we are kind of showing you over here. One such example is a 240 watt power supply, which I'm going to show you next. And that will be the first product that we put out into the marketplace. So this is our 240 watt product. That 240 watt product has 4 of the gallium nitride devices that I showed you in it. This is sort of a breakout of what that product looks like. And I have one of them over here that I will actually show on the screen. So this is our 240 watt product, and I'm comparing it with a HP 240 watt, 230 watt product that they offer in the marketplace today. And you can see the size comparison of how small we are compared to the HP product that's out there. Now the best part is that this entire product design actually happens in India. So we have a systems R&D facility in Bangalore that actually makes and puts this entire subsystem together. So we make our transistors in our Syracuse fab in upstate New York. We ship those transistors to our facility in Bangalore. The Bangalore team puts this entire system together, hardware, software, magnetics, everything that thermal design, everything that goes into it. And we have a contract manufacturer in India as well that actually contract manufactures this entire system for us, and then we ship it worldwide from there. One of the points that was brought about was efficiency savings, and I want to reiterate that over here. So the power supply that I showed you, which is one from, let's say, HP, Lenovo, or Dell, they're typically 88 points of efficiency. Our 240 watt with the vertical gallium nitride device is 94% efficient. And if you have a 6% improvement in efficiency and you make these simple-minded assumptions, you're looking at saving 391,000 metric tons of carbon dioxide from going out into the atmosphere. And as we pointed out earlier, if you have a 2% efficiency gain on pretty much every piece of electronic equipment that's there on the planet, you can actually save, you don't need to deploy roughly 97 coal plants in the marketplace. So not only do we make power supplies out of this, we actually make power supplies that go into data centers, and we have made it so that our power supplies are extremely scalable, so you get the efficiency benefit as well as making sure that the right set of devices get used in the systems that you put into the data center. The same thing works for automotive. There are 3 systems in the automotive: the onboard charger, the DC-DC converter, and the AC-DC inverter. These are the system savings that we actually bring on each one of these subsystems, especially with the 1200 volt device that we manufacture and put into production, again, into the same fab that I showed you before. We also work in the LED lighting space. This was another one of the applications that we talked about before. So we make the little LED driver that actually goes behind the LEDs, which put out the light, but you need a power system or a power supply that actually drives them. Every system that I've shown you here runs at 1+ megahertz switching frequency, and our devices, like I said, can actually do 10. So 1 is the starting point, and we're basically scaling it up. This is the company. I wanted to point this out because we are located worldwide. The key point here is that our R&D facility is in Bangalore. But one of the key points I wanted to talk about when it comes to building fabs and why the government program is actually so important is because building a fab and working on semiconductor technology is not like working on software, where the capital investment and the capital requirement is significantly lower. So you can have a team of 50,000 people, each of them having 1 computer each, and deploying a small number of servers to actually make sure that the entire team can work together. Setting up a fab is hundreds of millions of dollars of investment. This investment cannot be done over a short period of time. So the outlook for semiconductor and developing semiconductor technologies and fabs is a 10 to 15-year outlook. Such an outlook can only be supported by the government to start off with. So it's very good and it's very welcoming to see that the government is taking an initiative in reducing the cost of this initial capital that will be required to deploy fabs inside of India. But in addition to making sure that we have a fab and we have capital for that fab being subsidized, we also have to make sure that we attract the right talent and nurture the right talent in order to make sure that these fabs can actually run. You need process engineers, you need chemical engineers, you need people that understand device physics to all be coming together to develop a particular technology inside a fab. In addition to that, you actually need significant infrastructure build-out. What that means is the gases, the chemicals, all these have been discussed in the last few sessions, and Seema pointed this out as well, which is if you don't have the basic infrastructure that is needed in order to run a fab, you're not going to be able to make the progress that you need. So building a fab is a major undertaking. It needs the support of the government, so it is very great that the government is actually taking that step forward. But it's going to take a fair bit of time in building out a fab, establishing it, making sure that you just don't have one fab but multiple fabs. Around the fab, you need to make sure that the right talent is built out, the right talent is nurtured. You have the right university and industry relationships in order to make sure that there's a constant flow of people being able to work in the fab and produce the kind of technology that is needed. Doing this for compound semiconductor is even more complicated than doing it for silicon because compound semiconductors are new, and making sure that you understand how the compound semiconductor industry works, the process works, will also require additional training and resources and skill sets, which have to be developed inside of India in order to make sure that you can have a successful compound semiconductor initiative and a compound semiconductor fab. With that, I'll turn it back to you, Vivek.
Thank you, Dinesh. So as well, the lunch bell has been rung twice, and there is a reminder. So thank you to all of you. I will quickly summarize the session, and in case there is any time to ask the question. So first,
offline, sir.
The need of energy efficiency is very clearly established. There is no way, and I will just mention one more thing, that there is a target of 45 reduction in CO2 emissions from 2010 to 2030. So therefore, there is no way that we can escape. And great news is that these wide band gap material and transistors are available and solutions are there. Another key element has been mentioned is really on the ecosystem, that we need to look at it in totality, not in isolation, including the supply chain, otherwise it would not work. Third point, which is again highlighted very well, that manpower-wise, there is quite a lot of, let's say, strength in India, but we need to continue and also develop the electronic systems so that the whole ecosystem becomes richer. So I am sure I have not done the right justice for all that, but quickly, in sake of timing. So,
yeah, sir, with your permission, I think we'll have the questions offline. And sorry for that. And also because of we are behind schedule, the motivational injection prior to lunch will be done after lunch. So we'll break for lunch, and the motivational aspect you can take offline. The questions panelists will be available. You can take it offline.